spaceship production, talk about the community that has to come together, and then also that no, it really has to come together. Resolve there's only a little more visual to it, but not in bullet.
And morning, everybody. I'm Major Steve Verleski, and welcome to our second day of our Innovation Culture and 3D Printing event. Today is a little bit shorter than yesterday. We're going to focus a little bit more on the 3D printing, the materials of 3D printing, and 3D scanning, so that you guys can get a little bit of an intro to that. I want to thank the people that we had yesterday that aren't going to be here today, Miss Adrienne Cloud of Spark Macon and Mr. Robert Manning of NASA's Jet Propulsion Laboratory. You can check out his talk. We lost some of the audio on yesterday. But you can listen to most of his talk on YouTube if you just go to our YouTube channel, which is a great segue. Follow us on social media so that you know when we're doing events like this in the future. We're all here in the Spark Hub at Robins Air Force Base because we're trying to build an innovation culture. We want to bring every airman from their workspace and see if they can do things better. We've got three basic ideas. We've got that we can do things better. The Air Force does things old ways often, and new ways of doing things are coming out every day. Everyone knows that. So we want to make sure everybody knows if there's another way to do it, we want to know it. We want to help you get there. Also, every airman has a skill set that they can help bring to the fight. We want to bring you guys into the Spark Hub or to anything that lets you solve problems at your unit level, your shop level, or sometimes even at the Air Force level. We can do things better and everybody can help do it. And the last thing is we want you all to come in here so that you can fail. That sounds like a really odd way to say something, but we want you to get to success through failing. Every time you try something and it doesn't work, we want you to try again. We want you to knock it off and try again. This Innovation Hub is a place where we hope that you can do that. Robins Air Force Base should be a place where you can try, fail, and try again until we get to a right answer or decide that that's not the approach that we want to take. So if everybody can swing by, try to print something on our 3D printers, we'd really appreciate it. For everybody else at the other Spark Hubs all across the Air Force, if you guys are watching on YouTube, we appreciate you guys tuning in. Find the people that are innovating on your base and go to their Spark Hubs. They can help you do things that you didn't know that the Air Force would let you do. So moving on into the day, like I said, it's a little bit shorter. We're going to have Gary Hart and Jay Flesher come up from Firestarter Fab Lab in Middle Georgia State University. They're going to talk about 3D printing and a lot of the things that they have made possible by 3D printing in their Innovation Hub out in Macon. Also, we're going to have Joint Base Andrews in their Innovation Hub talk about 3D scanning and some of the ways that you can create new items from old items and how you can create large room scale scans of things so that you can either 3D print or use those things to innovate or do your own job. And then finally, we're going to have Kyle Acevedo and Jonathan Holmes from Georgia Tech's Research Institute, who are some of the experts on how to do additive manufacturing. They don't even call it 3D printing anymore. It's additive manufacturing, and they do things with minerals, or metals, and urethane, and all sorts of things that you probably didn't realize were possible. And they're going to help walk you through some of the process to doing some of that. But I just want to say thank you to everybody that's tuning in. I want to say thank you to the crowd here. We really appreciate you guys being here. And then I'm going to bring on Gary Hart and Jay Flesher. Cool. Guys?
Good morning. How are you guys?
Good morning.
So my name is Jay Flesher. I am with Slick Energy, which is an electric co-op here in the Middle Georgia community, and I do community economic development for them. Part of that was finding a grant that actually helped me stand up what this Firestarter Fab Lab, and we'll share that in just a second. Gary, you want to introduce yourself?
Yeah, I'm Gary Hart. I'm with Middle Georgia State University. I actually do military affairs out of Middle Georgia State. However, back in November, December of last year, Middle Georgia State answered the call for innovation throughout Middle Georgia, joining up with, University like Mercer, with Robins Air Force Base, with Firestarter Fab Lab. We created the Center for Software Innovation. So it's a small shop right now. It's growing, but we have a lot of dedicated faculty and students. It's all volunteer, just like here, everyone coming over to try and build something better. Yeah, that's where we are.
So we're going to talk about 3D printing, but a lot of what we're going to talk about too is the development of a community, because in reality, you do have those that have skill sets, and that was very well pointed out. You do have people in your community that have skill sets, and they're trying to solve problems where they're working. But they also, what's great about innovation is they want to solve their own problems. They're trying to they identify a need, or they identify something around them they want to fix, and giving them the ability to empower them to how to solve that. So real quick, I want to share with you what the Firestarter Fab Lab is.
How are those New Year's resolutions coming along? Well, maybe you have a great idea, but you just don't know how to get it off the ground. Maybe you wanted to learn a new craft. Well, over in Houston County, you can accomplish those things at the Firestarter Fab Lab.
I'm taking you inside to show you how some people are getting a lot more from those classes than just a new set of skills.
Any kind of knowledge they have, any kind of ideas they have, they can take it and run with it.
At the Firestarter Fab Lab in Houston County, people can see their ideas come to life. People like Ramey Chanel, a hobbyist turned entrepreneur, thanks to his know-how and the Fab Lab's resources.
We started making cutting boards, and I was laid off from my job the day that my business went live, and when it went live, it took off. I've even shipped to the Dominican Republic.
Now he's helping others to do the same, any skill level, any age.
From 14 all the way up into 80.
One of those is Karen Lloyd.
I love creating things.
But because of health challenges, that hasn't always been easy.
I've been diagnosed with lupus for over 15 years. You can't work 40 hours a week. You have a brain in your head that you could use. What do you do with that? And then I find the Firestarter Lab.
At the end of the day, our goal is really to take our community and move from a consumer community into a producer community.
Organizer of the lab, Jay Flesher, says they wanted to give people hands-on training and hopefully inspire more businesses here in Houston County.
By giving them access to tools and giving them the knowledge of how to do that.
From welding to woodworking to printing, just about anything you can design here on the computer can come to life right here.
Probably one of the greatest things I've ever done. It was awesome.
Lloyd came to the lab wanting to learn something new, but since then, she's left with a lot more than her creations.
Really give me self-confidence and a sense of purpose in life, that when you're sick and you do face challenges, that sometimes you don't feel like you have.
So whether it's creating a future business, tackling a hobby, or a newfound sense of pride, anyone can learn to blaze some new trails.
This is very empowering.
The lab is hosting an open house on February 7th. It's located at the Houston Career Academy.
Instigation. I mean, we're not going to certify you hardly anything. It's not about certifying you. It's about instigating. Hey, I can do that. I want to learn how to do metalworking, or I want to do how the digital side of woodworking or or CNCing or 3D printing. So that's really what the goal is about the Fab Lab. So originally it started as a issue around BRAC. Believe it or not, in 2012 there's a BRAC study came out, said, hey, we need to have an innovative society. We need to recruit and retention of STEM professionals. We need to organically grow STEM professionals, and we need to change and diversify our economy. Well, that's where the idea started to branch of this. And that's the reason why a company like Flint Energy said, hey, this is important to us, because we want to support, not only do we support what's going on inside the fence line, but we want to support the diversity going outside the fence line as well. And then one of our key partners is the school board. We're trying to foster that STEM development. We're trying to foster that kid that sits in his house or in his basement, and he programs all the time, but he doesn't project that out into his life every day outside of his basement. So we're trying to draw those folks out as well. So that's really what this was initially about. But then in the midst of doing all this, because the Fab Lab's been around for 4 years, in the midst of doing that, then you have a global pandemic come up. Our operations shut down, just like everybody else, it shut down. But then with that said, you start to have needs arise. And one of the needs arise was talking about some of the PPEs. So from my perspective, I tried to keep Firestarter out of the PPE production. And the reason why I say that is because once you turn that animal loose, I mean, it's all or nothing. There's no, once you start, there's no drawing back. But then a quick call from JVIZ and Spark Hub here at Robbins sort of lit the fire. And that's where Gary and his group came in as well.
Yeah, definitely. So, I mean, just like Jay said, earlier this year, there ended up being an international call to arms for personal protective equipment. So that, different organizations inside and outside the fence, PPE means something different to everybody, right? But when you look around at who was asking for it, initially we're talking, first responders, you're talking some of your medical communities. There just was not, we weren't able to produce as a community, right? So I will say that JVIZ Card and his folks here are part of some collaborative efforts and some networking that, when they reach out to each other and they're like, hey, we're doing this here, they take off with it. So while Firestarter Fab Lab, in my opinion, was kind of a hub on COVID relief, on PPE generation, I will say, and again, said this yesterday, and it's no pun intended, but the Spark Hub here started, it was a spark for getting PPE generation going here in Middle Georgia. So having said that, Jay reaches out to the network that he's actually set up here in Middle Georgia for Mercer University and their ability to engineer solutions. Maybe not so much on the mass production effort, but their engineering folks over there to come up with solutions for us to be able to produce, huge. Jay also reaching out to Firestarter, right? So now you've reached into a network of not only a Middle Georgia community hub of innovation, but all the spokes that come off that hub, which are the private citizens out there that are doing 3D printing, that are, I mean, you name it, they're creating products every day that we're just not thinking about, right? Further that, reaching out to Middle Georgia State University. Now at the time, again, like I said, it was the end of last year that we actually came up. We didn't have 3D printing. There was a lot of stuff that we didn't have. We're able to work through helping solve problems through the use of software, right? However, this spurred us forward in the need for us to be able to grow our innovation piece out of Middle Georgia State. It's fortunate because at the time, when we went out to get all of this, as far as being able to buy printers, being able to buy filament materials, all the logistics that came behind that, if we had waited any longer, we'd have been 4 to 8 weeks behind everybody else. But because people like Biz and the team out here saw an opportunity to be able to help our first responders in the Middle Georgia community, he reached forward and said, hey, we got to start this now before we start to fall behind. We did. And I will tell you, between Spark Hub out here, Firestarter Fab Lab, and all of the collaboration efforts that went on with the other universities and with our private partners, we were able to help a lot of people. I will tell you that this list right here, when you're talking about supporting, this is a taste of who we were actually able to help. And now I know you personally got to go out and distribute, actually hand deliver some of these things out to the communities out there. That's got to be huge. So when you're in on the production piece, right? So you're working, your head's down, you're not really thinking about it. It's just day in, day out. But you actually get to go out and see these folks as you're delivering these pieces. Jay, you want to talk about how that was?
Well, what's interesting is, I mean, it wasn't only medical folks, it was first responders, it was state agencies, it was everybody that's trying to go and secure PPEs, because at that point they weren't to be had. It was either already allocated or supply was already dwindled down. So within that, you see a huge group here that's a sample of it. But you know, in reality, when you start talking about what was being delivered, you know, we did 7,000 face shields. Now, not all those face shields were 3D printed, because in reality, you know, when you build a community around this, you know, and you don't already have a whole stack of 3D printers, you actually have to go out and find people in the community that have them and inspire them to come in and become a part of your leadership team, part of your guru team. And then you have to build your whole profile of production. And that's what we'll talk about a little bit later in this slide presentation. But this is a little bit of what we did. We did 26,000 pieces of PPE. Now, some of that was produced by 3D printers. Some of it was done by lasers. And some of those are components that you had to have all three of those components together to actually make the product come to fruition. When you build an innovative community, though, not only are they thinking about 3D printing as part of the solution, but they're also thinking about other ways of doing that. We did over 11,000 gowns. And again, that was part of your innovative community coming together to have a deliverable. You know, we did 7,000 tension strips. One of the issues that we had, and so many of you guys are having to do it now, is you're wearing face masks all the time. Well, in a medical situation, you know, and you're wearing it all the time, you start to cut behind your ear. Well, what we were able to do is we developed both a 3D printed model and a laser cut model of a tension strip that allowed that pressure to come off your back of the ear, which made that a lot more comfortable. So again, when you start talking about an innovative community, now in this innovative community, there are people in this innovative community that some of them know how to use the digital format for 3D printing or laser cutting or CNCing. But there's also, when they come together with a purpose. And that's what this slide is really about. It's about a community of purpose. Is the deliverables, I mean, what we encourage you to do is build your community, you know, inspire your airmen to come in and build this community of purpose, which actually allows for the deliverables to happen. So what happened when we got the call from JVIZ in Mercer University is we found this deliverable around a face shield design. And we needed to transition from the possibility, which is a one-off. We did a prototype of it, but then we need to expand. So what we ended up doing, again, is growing that 3D printing community. And we did an all-call on Facebook. And one of the guys that happened to be here today is Craig, you know, answered that call. And in reality, what happens is, why do you do this call? Well, we want, when you do a production like this, you need everybody on the same page. Now, you know, innovative people are great, but sometimes once they solve the problem, they move on to their own things. And in doing that, they come with great ideas. You know, here's an example of 3D printed masks that the guys came up with on their own time. They were solving their problem, but it was an innovative problem that they were solving for themselves and having fun with them. I mean, if you look at these masks, they're just outstanding, but it's not something that can be reproduced at a high level and produce that and put that out into a high volume. So again, look at the quality of these products, and they're produced on the same machines that we were doing as far as the mass brackets were concerned. But in making this all call, we had two guys show up, you know, Justin and you see him and Craig, because these are our #1 resources when it comes to putting a program like this together. I can tell you, I do what's best. I throw an idea out there, I find people that want to embrace it, and I hand it to them and said, you guys, tell me what you need. And that's what I did with these guys. And they really led the way on this. They developed their own Slack channel that allowed them to integrate with not only and recruit people in to have a singular purpose. Because again, for mass production, you want to not always innovate over and over and over again. At some point, you got to settle on a design and then implement that through the course of everybody so they're all producing it the same way. Why is that? Because you have other parts that have to fit into that. So if you keep innovating, the parts that you're producing outside of the 3D printing parts, they don't fit. So having a Slack channel and having that communication is a big part of what you're doing. So when you do that, we project into having 2 to 3 people that are doing 3D designs and printing. So all of a sudden you do a test run and you set up the production side. So you do the 3D printing, you mass produce enough of it to see if it's a repeatable process. You start to refit. With our lasering process, we had to have face shields, and that's where our friends at Georgia Tech and Coca-Cola came together and gave us PET in an 1,800-pound roll. Again, a very large roll, and how do you break that down? And then how do you continue to make sure that the pieces fit? And another one is we talk about the digital design of 3D printing, but also the 2-dimensional design of lasering so that you have a face shield that fits your 3D print method there. Now, when I say community, this is a big part of that. You know, again, you got an 1,800-pound roll of PET come into your community that you just can't handle just by anything. So having resources online in your either on base or outside the fence line that are willing to step up and help you, and that's what these guys are doing. They were using more industrial and commercial equipment to help us break down this big, huge roll of PET, so we're able to do this to make it fit our process. Also led to the need for zero touch. You know, if you guys remember early on in March, it was about little contact as we could have because we didn't know how it's being transpired or transmitted as far as the coded the bug was being done. So we did a zero touch drop off. We had the guys put their products in a bag. So we were able to set it aside and let it rest in between deliverables. We were able to do an inspection on what was going on, but we always had in mind that this process was not the end goal. I mean, it filled the gap, but eventually you have to go from a prototype to micro production that you want to eventually go into normal production. And for us, that the end goal was getting into where we were using injection molding. So it's really think about it when you're solving a problem. Is it reproducible, and does it lead you to the next goal, which is higher production of manufacturing in a traditional method? Then the final piece of that is the deliverable itself. So we're taking it from a zero drop off. We were doing inspection and packaging, and this allowed us to do a packaging, and we actually delivered over 1,000 3D printed face shields. In other words, the brackets 3D printed, and then we actually cut the face shield on the shielding material off on the laser, and then obviously marketing, because we want people to know that what we're doing is available to them. So that's the other side of it. So when you do that, when people find out that you're being innovative and producing things that can't be found, you start to get calls. You start to get calls from the community. Now, if you also remember, part of the PPE process was there weren't face masks. You couldn't get face masks, the actual face mask itself, hardly anywhere. So all of a sudden you had the sewing community come up and start sewing face shields, face masks. They were given to hospitals. They were actually, I remember actually delivering about 1,400 face masks out here to the base for training purposes. And part of that is when you do that, you have sewing groups that were standing up. Well, you again, just like 3D printing, you want it to be a repeatable process. So the product is the same every time. Well, part of that is in the pleating process, not everybody's a great sewer, right? Because you had people that may have been the first time they got their sewing machine out. But what we did find is through open sourcing, we found a couple of things that made huge impacts. So this is actually a pleating tool that allows it to pleat up, and that was the style that was being done, and sort of was the style that people were accepting of. So you put all of a sudden somebody that didn't know how to do a pleat, give them this tool, and then they were able to start sewing it, and they were actually able to step into the fight as well and do what they could. Well, the other thing is you couldn't find elastic. So you can find the material, but you couldn't find the elastic to go around the ear. So what do? Well, you go out and you find a bias tape tool. Well, this bias tape tool was old school. What it allowed to do is you could put a piece of material in it and it wrapped it so that it could be sewn or glued as a tie around the back of the head. So we're eliminating another problem. We couldn't find elastic, so we couldn't put it, hold it against somebody's head. Now we're doing with a bias tape tool that allows somebody to do that, add a skill to their list that we normally have. So we did actually about 1,500 pieces of both these products. That imagine that, if they were using this tool, they were actually putting something directly into the fight versus COVID. So again, answering the call through innovation is part of the process. And then one of the final things that happened is again, towards the end, and just recently, we had a band director come to us and said, hey, normally what we end up doing is when school gets ready to start, since we would normally have all of our middle schoolers come in and they would choose an instrument that they want to do. We would use the normal mouthpieces to have them test it, and then we would sanitize it, and the next person come in and they could choose which one they wanted. Well, this couldn't happen based off the normal circumstances, and the reason why is because of the sanitation process that needed to wait. So one of our middle school directors here in town said, hey, I've got these 3D printing open source mouthpieces. Can you print them? Well, again, having people like Craig and Justin, you shoot them an email and says, hey, can we print these? And they're like, oh yeah, we can print this, but will it work? So it's just like, again, you're taking the open source design, but then you have to vet the process of making it work. And one of the things that we did do on that, and I'll show these around to you guys so you can actually see it, is we did some printing on different filament and different machines, and then came up with what worked best and the deliverable. And then we had the band director actually come in and test these. So that was a big deal with these things, was allowing it to be vetted by the band director, and then a deliverable be sent to them. Well, after that happened, we started mass production of these. And so we actually, all the middle schools in Houston County and in actually some in Peach County were delivered these mouthpieces to go ahead and recruit, retain, and encourage their kids to come in as band directors. So with all this said, it leads to lessons learned, because we're trying all the time. We're trying to innovate through a moving target. And so when that happens, you have to think about what we did wrong and what the accomplishments are. We'd like to talk about the lessons learned.
Now, come on, we're talking military. So y'all definitely know lessons learned, hot wash, whitewash. That's what we had to go through, right? Because when all this started, it caught us off guard. We recovered quickly. However, Jay talked about it earlier. When you have all of these different folks coming together with their different ideas on how we should proceed, you got to get a handle on that quickly. Again, luckily, we've got folks like Jay Vizcarra and the team here, the folks out at Mercer, the folks at MGA, folks at Georgia Tech. Again, it's all these folks coming together quickly and deciding on things that we need to do in concert that made us successful. So again, we did really good at it, but I'm sure next time, whatever that is, we're going to do even better, because we've actually lined up the process. Next, it's getting everyone to work on the same product, right? So if we're building up a gun and everybody builds up a firing pin, we're not going to do too well, right? So again, getting everybody together, figuring out what products we need to work on, and the ability to take those leaders that volunteered, to get them to break up into teams and take charge of those teams to bring those products together, so that then we can go and put together the storage piece and the distribution piece. So that mass production, right? It's a lot of work. Luckily, again, we had a lot of great leaders throughout these organizations that were collaborating together to be able to bring all those folks together, keep everybody on target, and keep everybody coming in with the pieces that we needed so we could get them all together, get them cleaned up, and get them back out. But I will say that, again, one of our biggest things, storage and distribution, right? Jay, especially when we had the no-touch drop points over at Fab Lab.
1,800-pound rolls of PET coming in, boxes of injection molding brackets. You know, when you start to have all this product come in, it's important to have an organized process to do that. Again, it's about your innovative community. I mean, yeah, you're doing 3D printing, and we're talking about 3D printing today, but in reality, when you get this community together, you know, empower them to use their information, the things that they do every day, to empower and make your community a better place and more efficient in its operation. Not everybody knows everything. Not everybody's great at woodworking. Not everybody's great at digital design. Not everybody's great at 3D printing and understanding the scanning model. But if you have enough of innovation in that mindset of innovation come together, and all of a sudden the answers sort of start to being provided, because everybody's thinking outside the box, which is exactly what we want you to do, is think outside the box. Although, you know, sometimes you work in restricted type of thought processes, and you have to when you're inside the fence line. But also, you know, think about just because you're being restricted a little bit, that doesn't say that you can't be innovative and you can't think innovative and ask questions as to how it can be delivered.
Now, real quick, so you think about it, much like RPA, right? RPA, drone operations, that's all in its infancy. And everybody's like, well, it's been around. Yeah, it's been around for 20 years that some of us have worked with, right? That's still infancy. You talk 3D printing, it's still in its infancy. We've got some awesome organizations out there. You heard earlier, Georgia Tech, you've got folks out there working with metal, right? But who's been downrange with a downed aircraft that can't fly back because you're waiting on parts? Again, that's the kind of stuff that the Air Force is working on now in collaboration with its partners out there, to be able to get these parts down there where you need them, with maintainers being able to build them right there. Oh my gosh, you've changed the game. Y'all are part of that. So again, as airmen and as people on this side of the fence, no matter where you are, get into hubs like this so that you can help, because that's where all the ideas are not coming from some of us older folks, right? It's coming from the generation of outside the box thinkers. That's y'all. So
yeah, absolutely. Absolutely. The community delivers. If you give them a problem, the community will deliver. So what I can tell you, the next slide is actually a quick video about the results that we had coming out of the COVID.
Nikhil, as the need for personal protective equipment increases, some healthcare workers might find themselves without critical pieces of that equipment. Well, Firestarter Fab Lab in Houston County decided to fill in that gap and give those on the front lines the tools they need.
Our medical groups to battle this pandemic. I mean, they're in a war, and they need tools.
Jay Flesher with Firestarter Fab Lab, a nonprofit innovation lab, says when he was made aware of the need for personal protective equipment like face shields, he knew the lab could answer the call for help from those on the front line.
We're sitting here at the Houston County Career Academy with $300,000 worth of equipment and volunteers that know how to run it.
Volunteers at the lab, along with community partners, started making face shield brackets along with mask tension strips to ensure healthcare workers had the safety and comfort they deserved while fighting COVID-19.
We'll put a face shield on somebody that needs it in a critical situation, and it will save them, or actually save the PPEs that they're using that are really, truly critical.
Flesher says it isn't only about the physical health of those on the front lines, but their mental health as well.
If we can give them a little bit of security, a tool that they would not normally have because it's not available, then I think we've done our job.
So far, they've made 6,000 tension strips and 350 face shields with the help of volunteers and donations. But Flesher encourages the 3D printing community to do more.
With us and find out what you can be printing on your tool, on your manufacturing tool, and then get your piece of equipment into the fight with us.
Flesher tells me coming together as a community right now is essential, and it tells our healthcare workers that they aren't alone.
So again, building community, but also finding your funding sources, right? So inside the fence line, sometimes it's a small win. Find small things that are deliverables that you can create value inside the fence line that might lead to either one, having someone in leadership say, yes, what you're doing it has an impact, so we want to help you. It might be just a quick confirmation or affirmation that you're valuable to them and they understand the culture that you're trying to build. Or it may even lead to funding that helps you process the thing, because that's where it all goes is to do this stuff and have this equipment and have a set aside like a Spark Hub here. It comes down to funding. Do you have funding to make that happen, and do you have the support of your leadership to make that happen? Always ask. Always give that person, when you're doing a brief, a way to engage with you, either in support of funds or a support in word that leads you to the next opportunity to gain that traction as far as the project goes. So that ends the brief a little bit. Thank you for your time. Would welcome any questions you guys might have.
We actually have a question from YouTube. So there's a question from CF Gibbs. What is the sign up and the reservation process to use the Firestarter Lab? And also, what is the minimum age to use equipment?
So different equipment is different things. So in reality, on the digital side, that if you come in with skills, it's basically you can have as easy as walking in and paying a $10 charge, and then the product fee on the product you're using, like filament or whatever else. We have multiple machines in there for you to use as far as the digital side and the 3D printing side. We also have lasering. If you have skills around the lasering side, it's as easy as going in and checking out with one of our gurus that you know how to operate it, and then using it. Now, when you start talking of the woodworking and the metalworking side, there are some classes that have to go on with that to make sure you're using it in an appropriate way. But those skills, that training leads to make sure that everybody starts in the lab at the same level when it comes to the woodworking side of the thing or the metalworking side of it. Again, if you have those skills outside of woodworking, if you have the skills for welding, or if you have the skills for the digital side of things, it's as easy as coming in, paying your fee. A monthly fee for military is around $30. It gives you access to the full lab, or a day pass is as much as or as little as $10. So you're able to do that. If you go to firestarterfablab.com, and that will give you all the information as far as the Firestarter, both class structures and also fees are involved.
And they're on Instagram at Firestarter Biz.
Yep. Also on Facebook, Firestarter Biz.
One of those millennials.
All right. That's good.
All right.
All right.
Thanks, guys.
Thank you.
So who here, just quick show of hands, hopefully we got the crowd cam up, but quick show of hands, who here has 3D printed something? So there are people here who haven't, and I just want to open the doors, especially in honor of our 3D print workshop. We're going to open our doors. If you guys have people in your shops, or if you yourself want to swing by and print something on our 3D printers, come by. It doesn't have to be something for your job. You can just print a pen holder if you want. If you're one of those dudes who wears a pocket protector, you can probably 3D print one of those, because we're all nerds here. Also, I want to make sure everybody here in the crowd knows we're going to have lunch, but we're going to take a quick 5-minute break. If you're on YouTube, I can't get you lunch. I'm sorry. But we're just going to keep on innovating. Unless there are any questions for me, let's go to a quick intermission. So it's Westfield from Joint Base Andrews. What they've been doing a lot with is 3D scanning. And what they've learned is there's a ton of applications and a lot of things that you probably haven't thought of for 3D scanning that, that can cross a lot of disciplines. All right, welcome back to everybody on YouTube. We're about to bring on some people from Joint Base Andrews Spark XL. Sergeant Andy Renteria and Master Sergeant Laura Westfield. They do a lot of 3D scanning. They're going to talk a little bit about their process, but also some of the really exciting ways they're applying it. So without further ado, Andy, are you in the call yet?
Hey, we're here. Can you hear us?
Hello.
Oh,
yes.
Can you guys hear us over there?
All right. Cool. All right. Can you guys hear us?
Perfect. We can hear you fine.
We can't hear that.
Uh-oh.
Do we have a speaker on? Are you guys muted?
No.
No.
We're good.
Okay. We don't hear you, but they're hearing us, Jay. So. He hasn't. It's turned up. So, is there any way that we can use one of the Sonos speakers to start it out? Please bear with us while we solve a technical problem.
Yeah.
Sure, no worries. How's everyone doing?
I don't think they can hear us.
Oh.
All right. I think we got it.
Perfect. Can you hear us now?
I can hear you guys now. All right. I'm going to give you guys the stage. The floor is yours.
Sweet. Yeah, well, it's a pleasure to join you guys today. Looks like we've got quite a few people over there. You guys doing all right over there? You staying awake? Feeling intrigued? Well, my name's Andy, Sergeant Renteria, and this is my colleague Laura. And we're going to talk to you guys a little bit about 3D scanning today. Just to kind of give you guys a little look around our Spark cell. This is our little idea center. And this is where a lot of our printing, a lot of our scanning happens. And let me ask you guys a question. Can anybody tell me what type of applications they use 3D scanning for these days? Anyone?
PPE.
I can't hear. What's that?
PPE.
PPE? Yeah, PPE is one. Let's bring it down to a little more surface level application. How about stuff like gaming? So with a lot of games these days, they actually do a lot of 3D scanning for that. Anybody into cars over there? Yeah, so if you're into cars, a lot of applications like building aftermarket parts for cars are based off of building via CAD and 3D scanning. So we come over here. We actually have a couple of pretty cool scanners over here within our facility that we actually use. So we have this Artec Leo 3D scanner that we use in-house, and this thing is a beast. I'll actually talk about this one in a little bit. This scanner, this is the Peel 3D. It's a Canadian-made scanner, and this thing is super portable, and the renders that it produces is pretty awesome. One of the things that we've been using this scanner with has been prototyping ideas for units such as the flyers. So one of the tasks that we've been working on has been scanning parts from jets and trying to reproduce them through our CAD programs and seeing if we can actually print something like this in the event that something breaks. We've actually had the opportunity to work on a couple parts with Air Force One, which has been pretty cool, and different units all across base. There are a few limitations that we actually have though, which are getting things FDA approved or anything that's safety related on jets. We haven't quite gotten to that point yet. But one thing that we have done over here has been for our 3D masks. When it comes to 3D masks, or actually, let's start from the beginning. When COVID first kicked off, we were actually able to find a lot of files online of 3D masks, and we started printing them. And at the time when it first started, there weren't too many versions out there. So what we started doing is we started printing all different types of masks, and we found out which ones worked and which ones didn't. And over time, we started getting different models. We started adjusting them ourselves and started trying to kind of change them the way they are to get them to fit individuals' faces. But one thing that we learned is that not everybody has the same face or facial structure. So we started doing different things like getting putty to work around the masks, molding them to our faces, which seemed to work for the most part, but it's not really the cleanest product. So what we started doing is we utilized our 3D scanner here, and we were actually able to scan people's faces and get a 3D image of themselves and get one of these masks and actually overlay it over their face and get a perfect fitting just for that person. So if you come over here, I've actually got an example up here on the computer. It's right here. This is Chief Wright. He actually came down, he toured our facility, and we had the opportunity to actually show him how our process was done. And we actually did a 3D scan of his face. So if you look right here, there he is. And look how good that image came out. It's almost unreal. Probably hard to tell on camera, but man, it is awesome. So what we were able to do was throw our mask on here and throw his face on here. And then we were able to move him through and basically fit that mask specifically for him. And by doing that, he then had a one-off mask that had his name on the top and it fit perfect. This is a two-part mask. A lot of you may have seen these. You put the filter over it, and then you can close this on it to hold it tight. And yeah, so if you ever wanted a one-of-a-kind mask just for yourself, this is the way to do it. Now, when it comes to 3D scanning and all the different applications that you can use, which one thing I forgot to mention is Google Earth. If you guys have ever used Google Earth or Google Maps, you've done the street view on it, where you've done the over the top look, where you can zoom in and you have the 3D buildings. A lot of that's actually done with 3D scanning. It's all this stuff you don't actually think about until you actually need it. Well, for me, one thing that I actually do to try and increase my knowledge with 3D scanning in-house and just get better at this is I use my own test subjects. For me personally, I'm into cars. And one of the things that I did was I scanned my computer. Or I'm sorry, I scanned my car. So I was able to scan the front end of my car, just like so. And what I'm working on is doing a render of this. And by doing so, I can actually start making aero parts for it, parts to make it more aerodynamic. And so this right here is basically the rough draft of the image. And once I render it, it's going to look exactly like my car. And I'll be able to add whatever I want to it, and I can print it and really just get better at this, because we're by no means pros at all with this whole process, but we're getting better and we're finding different ways to use this every day. Now, we come over here, we got Mr. Zimmerman with us, and he's actually going to talk to you guys a little bit more about 3D printing and a lot of the applications that it can be used for.
Or 3D scanning.
Oh, I'm sorry, 3D
yeah,
scanning.
scanning. Let me see, where am I?
Yeah.
Okay, I got a good picture. All right. I'm Chris Zimmerman. We kind of, back in 2018, we developed this innovation center, SparkXL, mostly because we had some end of year funds. We had a very progressive thinking wing commander, and he said, get the things that you need so it strikes the imagination of our airmen. And you know, the technology that you see around, and I'm sure you guys see in your Spark cells, is great. It's fantastic. You know, people can come and work with it, play with it, learn it, etc. But it's really all about trying to build that culture of innovation. And I don't know if you guys do this, but you know, we basically tell all the squadron folks here, and it's a joint base, so we tell our joint mission partners as well. Hey, go back to your organization, go back to your shop, go back to your office, and ask yourself the question, what sucks? And that, if they can come up with an answer to that, they'll bring it to us. And one of those things was the 3D scanning capability that Sergeant Renteria was talking to you about. So some of the things that we're also looking at using the Artec Leo, the handheld device, because it's handheld, we're able to use this as not only a Spark cell asset, but also a base asset and potentially a regional asset. So if somebody needed to go on an aircraft, primarily our 89th MXG folks who work on Air Force One and other VIP aircraft, they have a problem because if something fails on there, like a railing or one of the president's waste baskets, or you know, the president's you know, dinner tray or something like that, or something that's attached to the inside of the aircraft, they, you know, if they need to repair it, they're going to have to go in and remove it, bring it back to their shop, they have a really poor, you know, 1970s type scanner that takes about 18 hours to scan something very small. And they said, well, with this capability, they'll be able to go on the aircraft, scan the part, bring back the scanned file, load it up into their CAD system, you know, touch it up or whatever, and then print, you know, basically create it with all the different machinery they have. So they have CNC machines, they've got laser engravers, you know, it's just everything that they have there, without taking that existing part that might be slightly broken or whatever from the aircraft. So that allows it still to be used and, you know, the aircraft to fly. So this is one of those, you know, great uses of this type of equipment. Another thing we were talking about too is we had a demonstration of all these 3D scanners back in August last year. And we invited security forces, we invited aviation safety, and we invited facility managers. And everybody was able to see how the Artec Leo went, or it was going to be used, as well as the Artec Ray. And we don't have an Artec Ray yet, but I'll talk to you about a little bit about it. So for the security forces folks, we had one of our captains lay on the ground in a like a dead body outline. So we got some caution tape and we outlined her body, and we put like a screwdriver stuck between her arms and a knife on the floor. And the security forces guys were like, oh yeah, if we were to come across something like this, we'd have to take down notes and take photographs and take pictures and then kind of piece it all together. So the 3D scanning company took the 3D scanner and in 3 minutes scanned the entire scene, not just her body, but you know, all the walls, the carpeting, the entrance to the bathroom area, etc., and built a whole 3D image, threw it up on our smart board, and said, okay, what would you guys do with this? And the security forces guys were blown away. They were like, wow, this totally, you know, revolutionizes our way of being able to look at incidents and you know, track them. So that was one pretty good use. The Artec Ray, and I'll just kind of describe that. It sits on a tripod, spins around 360 degrees. And as it's doing that, it's got a LiDAR radar in it that spins this way. So it paints a whole 360-degree image of the entire space. So when they came in with that and they set it up right here where I'm standing right now, in 3 minutes, they had a 360-degree scan of our entire space in color up on our smartboard. And that to me just blew me away. So we started thinking, how are these going to be able to be used? So again, the security forces said, well, if we have a traffic accident, we can take that out and scan the whole thing. The aviation safety folks said, wow, this would be great for an aviation mishap. So we can go out to a mishap site, get a bunch of 3D images all set to go, and fairly quickly before weather starts to deteriorate the accident site, animals start to carry away parts. The local populace and the emergency services that aren't Air Force related go out and start moving things, and et cetera. So that's a really great thing. Also, our facility managers on the base, we have, I don't know how many buildings or facilities here, it's probably more than a couple of hundred. They said we can use the Artec Ray scanner to scan the inside of buildings as well as the outside of buildings. And the company that built this actually scanned the entire Smithsonian Natural History Museum inside and out. And now they've got a complete 3D scan of that building. What good is that? Well, from a facility manager's perspective, they can say, oh, well, this is how our building looks now. It's a baseline. Now we can understand a little bit more about what's happening from a maintenance perspective and how we can, create new structures, new rooms, et cetera, to make it a little bit more efficiently used. And also, I'll go back to the Artec Ray handheld scanner. It has such good detail that it can actually scan keys, it can scan shower head parts, it can scan door handle parts. And then if we take those STL files and put them into either the plastic 3D scanners or our new metal scanner that we're going to get, we can actually create the parts that they need, which is great for them because sometimes those are proprietary parts. They either don't exist anymore, or they're on back order, or there's a 6 to 8 week delay, which minimizes the building's efficiency to run. So from those perspectives, start looking at, you can take a look at 3D scanning, and there's a ton of different ways to do this. And like I mentioned yesterday, I know Lieutenant Colonel Descaro was taking a look at putting one of those 3D 360-degree scanners inside an engine or an aircraft to just kind of build a 3D image of that and use that for a training perspective. So, your imagination is unlimited, compared to, for what you can do with these 3D scanners, particularly the ones that have, that strong capability. And I think yesterday, I don't know if you guys showed it today, but there's a piece of equipment that you can attach to an iPad, and you can actually do a 3D scan of the inside of a room, which is great. But it didn't do it in color, and it just basically built a CAD drawing so you can actually manipulate it and put in the furniture, remove the walls or whatever that you want with that. The beauty about these fairly more expensive pieces of equipment is we can use them proprietary. We can use them on aircraft, et cetera, without any hesitation. So with that, I will open up the floor to questions. So. And that'll be for me or Sergeant Renteria or Sergeant Westfield.
We've got a question from YouTube. A lot of our audience here at Robbins is maintainers, and there are people who are considering maybe hopping on this particular innovation train and acquiring a scanner for their own shop. Which ones would you recommend? I know one of the ones that comes up often is the Einscan Pro.
Yeah, so the Einscan Pro, as I mentioned yesterday, that's a very nice piece of equipment, but it's made by I think it's called Shining 3D company based out of Wenzhou, China. So the Einscan is not a US or NATO product, or it's made by a company that's on the good list. So you got to be very careful about what you purchase. And one of our organizations on the base here, they purchased a 3D scanner or a 3D printer, and it was actually bundled with an Einscan 3D scanner. And I said, hey, great that you got that, but really you shouldn't use it, especially if you're going to go on, VIP aircraft. And they're like, oh. So they kind of wasted a bit of money, even though it was bundled. So you got to be very, very careful about what you're buying, particularly if you're using it on in areas where they're sensitive. So from our recommendation, I recommend the Artec Leo just because it's made in Luxembourg, and it's a very reputable company, and the piece of machinery is phenomenal. Like Sergeant Renteria showed you, it's got very high quality. It has onboard processing capability. It's got its own battery with a fairly long life. You can take it anywhere. The problem is using it in sunlight. It's a lot more difficult because the 3D scan technology right now just doesn't pick up the objects in sunlight. So you have to kind of play around with that.
Another kind of follow-on question is some of the units that we have here aren't ready to accept the risk as minimal as it is to buy an Artec Leo. Is there something kind of cheaper that's not made in China?
Yeah, well, so actually, if you guys wanted to just start this up and kind of just see where you can go with it, there's actually apps on your phone that you can download. There's several different apps. One of them that we tried was called Scandy Pro, and although it's not going to be as advanced as something like this, you can actually scan a pretty good image of anything and save it as an STL file, which is what we use on our CAD programs like Blender, for instance. So if you guys just wanted to get your feet wet and you want to try something different, feel free to download them from the App Store and try those out first. And you'll be surprised with the type of stuff that you can do with just your phone.
All right, and then we've got another question. So because this is kind of a new process, people expect that it'll be hard to implement, what with red tape and other, I guess, bureaucratical norms. So how did you guys get around some of that stuff?
Yeah, so I'm not sure if we actually got around it per se, because when we bought the Artec Leo, it was buying the piece of equipment, and it came bundled with its own software. So right now, I just had a discussion this morning with the AFWERX MakerForce folks, and we are putting together several white papers about how Spark Cells should be allowed to use this type of standalone software systems as well as standalone IT systems, because they're not connected to AFNet. So we're writing some white papers for either SAF-AQ or other members within the Secretariat within the Air Force to say, yes, Spark Cells should be able to operate autonomously and alone. Are we going to be able to get that done before the end of the fiscal year when some of you are trying to get your purchases sorted out? Probably not. But we are aiming for within the next fiscal year to make sure that at least people are aware of what the Spark Cells need. So,
so a lot of red tape yet.
Yeah, so there's some AFIs and some AFMANs that are out there that kind of dictate what we can and cannot do with standalone equipment that's not going to be connected to the network. And there are some other issues that we're working through. So it's if you haven't joined or haven't sat in on an AFWERX MakerForce meeting or an AFWERX Spark Cell update meeting, I think Colonel Vizcarra, he can probably set you up with when those occur. They're fairly useful and lots of good information.
And I know you guys mentioned the Artec spinning scanner, but from just your Spark X-Cell, are there any other purchases that you guys are planning in 2021?
Go ahead.
So many things.
Yeah.
The 360 is what we were planning on getting, right?
Yeah, 360 camera to create our own 3D and virtual reality environments. We also had on the books a circuit board repair and build center that we're going to put in our makerspace. That was lower priority this year, so it didn't make the cut. I am actually looking strongly into Microsoft HoloLens 2 as a way to either demonstrate or test the capability to expand our ability to do dispersed work environments like we're learning through COVID. This kind of falls off the saddle. This falls from discussion that we had during our Two Stars virtual tour of the Spark Cell that these two put together. He said, hey, I want to figure out how to work better and improve our way of working in a dispersed environment, because we've already proven in the Air Force that we can telework and that we can, still conduct the missions in a dispersed environment. So HoloLens, if you haven't looked at it, Google it. HoloLens 2 came out last year, springtime, and the Army is using HoloLens 2 for training its soldiers in battlefields. So they'll basically put this HoloLens 2 thing, and it's very lightweight, and it's just basically a goggle that goes in front of your eyes, and you can see holographic images, of whatever that you need, and you can touch and interact with them and press buttons and move things around. You can have literally a 90-inch web browser follow you around wherever you are. You can move it around, you can play a piano, etc. So the Army's looking at that from a battlefield perspective, and Microsoft has a contract with them. Air Force is looking at that HoloLens 2 stuff in terms of aviation maintenance, so aircraft maintenance. So they're building a HoloLens 2 version of that for training purposes, so people can actually, get into an engine and start working on it without actually touching an engine and without making it down, but it'll keep their readiness and keep their capabilities of being able to do that work. So, and we're also looking at it from a dispersed work environment perspective, so we can actually have avatars. So if we were all wearing HoloLens 2 right now, we would be able to walk in and amongst you as holograms, and you'd be able to interact with us. So that, say what's the operational requirement for that? I don't know yet, but at least it's a proven capability and would allow us to be present a little bit more than what we are right now.
All right, does anybody from the audience have any questions? Because we've got one more distance question. All right, and then so the last question that we had, I believe it was asked yesterday as well, but how long does it take to scan and replicate some of these things? Like what time does it take to go from scan to an STL file that you can then print or CNC or et cetera?
Yeah, that's also a good question. So it all depends on the size of the file that you're scanning, or the size of the object. The other day I scanned a whole version of my car, and it took maybe 3 hours to upload the whole file onto the system, and then to export that as an STL file, that took maybe an hour. So, but now if you're doing maybe someone's face, like we did with Chief Wright, from the time you scan that, now the cool thing about our scanner too, is that it connects via Wi-Fi. So you're able to scan, and as you're scanning it, it's constantly uploading to the computer. So by the time we completely finished that scan of his face, we were just about done uploading it onto the computer. So when you're able to do that and then export it, it just takes minutes, especially if it's something small like that. And then to take that file and put it on a program like Blender and make your alterations to it, and that all depends on your experience. But if you're pretty good at it, it's not going to take you very long. Now, the good thing about our printers that we have is they're fairly quick when it comes to printing. So depending on the printer that we use, we can print a full mask in the matter of maybe 30 minutes to an hour. Now, some of the larger printers that we have that print a lot more detailed objects, those may take a few more hours to print. So I guess from start to finish, I'd say about a day to get the full scan, make your edits, and do a full print. So it's definitely something I wouldn't recommend a smaller facility to start mass producing objects or masks or PPE, which it can be done. It's just a little more time consuming.
Thanks. And we've got one more question from YouTube. Have you guys built any partnerships with people who do kind of large scale, either 3D metal printing or your own 3D metal printing? It sounded like you mentioned that earlier.
Not yet. We're in the process of working with the 89th group. Those are the special organizations that work with the VIP planes. And so something in particular, like the seat, the covering for it, the way they measure it is in an analog format. And so we're working on getting the permissions to actually get on there and scan those objects.
So, and also we had the first iteration, or the first project that came out of the Spark Cell back in spring last year was a new surgical retractor tool. So our surgical squadron commander, Colonel Chambers, he said, hey, we've been using this Army Navy surgical retractor tool for about 50 years, and it's no longer fit for purpose because they have more advanced equipment that they use in the operating room. He said, hey, we need a new design. So he and a team of a major and a senior airman came in, used our facilities here, used Blender, and created a new surgical retractor tool. 5 iterations later, they printed it out in various things. It wasn't big enough. And we also needed it in stainless steel and nylon. So we called AFWorks, and AFWorks has a contract with UDRI, so University of Dayton. And we just basically sent them the STL file. And about 3 or 4 weeks later, the surgical squadron commander received a highly polished stainless steel and a ready to use nylon surgical retractor tool built and printed to their specifications. So it's not really a partnership that we have, but the connections that we develop throughout the whole Air Force innovation ecosystem and DoD innovation ecosystem has the capability to provide what we need. As far as other partnerships, we're looking at building a greater partnership with the STEM community around here in high schools and in colleges to get them to be able to come on and use our space. Right now, that's a bit of a legal battle because how do we let civilians use equipment and it's purchased with Air Force money? So we're kind of working on that as well. But yeah, there's a variety of different partnerships that are available.
Boston Dynamics is right down the road too. Yeah, so there are a few companies that we do plan on working with in the future as well. Boston Dynamics is actually right down the road from us, and also Boeing. So those are 2 of the big companies that we do also plan on getting in touch with, and just seeing how we can utilize their capabilities and see what we can do as far as helping them out as well. And so in the near future, we're hoping to work with at least those 2 companies, along with a lot of other ones that'll be coming up soon. So more to come.
Awesome. Well, that's the last that we had as far as questions, unless anybody else last minute re-attack. Besides that, we really appreciate you guys' time. We really appreciate all the questions. We had a lot of great questions today from the internet. And we really appreciate you guys sharing your expertise with us. For everybody here, we are already sending them a 3D printed clone. So we really appreciate their time. And if you got any ideas from them, we can help you get in touch. Well, we're going to go to a quick intermission, though, so that everyone can eat. There aren't any questions. Oh,
good.
Yeah.
Hey, I just wanted to say thanks very much to Robbins Air Force Base for putting this on, because this is probably a way of the future for us being able to provide, getting great training or great information for people who are interested in tech. So good on you for this initiative. Well done.
Yeah, and one other thing, if you guys also wanted to check out what we're up to, we also have our website that you can check out as well. We try and update it as often as we can. It's sparkxcel.com. And a lot of the links for the programs that we use, a lot of the CAD programs, our major's real big on coding. So a lot of times he'll put some of his links on there as well. If you're ever curious as to, learning some of the stuff that we're learning as well, feel free to jump in there and check them out too.
You guys have my information. If you guys send it to me, we'll share it to our Facebook page, and we'll make sure that everybody here gets some exposure to the things that you guys are doing here. We really appreciate it.
Yeah,
awesome.
Perfect. Thanks for your time, guys. It was a pleasure talking to you guys. Thank you.
Take care.
right, welcome back to everybody on YouTube and everybody here in the audience. We've got our last speaker for today from the Georgia Tech Research Institute. It's Mr. Kyle Acevedo. And we heard his talk yesterday, and I want to point out or draw attention to a couple things. You can do a lot more with additive manufacturing than you probably thought you could, but you also maybe shouldn't use it all the time. And he's going to talk a lot about that. But he's also going to talk about some of the things that you can consider while you're going about this. You can make just about anything with additive manufacturing, but how you do it and whether you should do it are things that he's going to really emphasize. So thanks for joining us, and here's Mr. Acevedo.
Thanks. Hey guys, my name is Kyle. I am a senior research engineer at the Georgia Tech Research Institute. And so GTRI, as we go by, is directly affiliated with Georgia Tech, the school, but we are on the applied research side. So we're responsible for taking some of the more basic research that professors and scientists do on campus, and we figure out how to turn it into actual systems. And so we do a wide variety of work, but over 90% of what we do is DoD supported. So primarily we're working for you guys and all of the other branches. I've been at GTRI for about 6 years now, and started as a mechanical engineer with a broad background, but in the last couple of years, I've really started to focus on additive manufacturing, and we've got some pretty cool sponsored work going on, and have been able to really get in on the leading edge of the technology and put it to use for the military and for the warfighter. So we do work with the Marines, we do work with you guys, and for all the branches really, but there's been a lot of investment in AM, additive manufacturing, and so it's been fun to see. So today, I guess I will be talking for a little while, I guess 2 hours or almost 2 hours with a break in between. But we're going to split it up into 2 parts. So part 1 is going to be just a general overview of additive manufacturing and what that means. And so, you know, I feel like if you want to be able to effectively use a tool or use a technology, it's good to understand the underlying platform and just the basics of how things work. And then we'll talk about when should you be using additive versus some of the alternatives that are at your disposal. And then for the second part of the day, we'll get into a little more of the nitty gritty and talk about some of the things that you should be thinking about and should be aware of when you actually want to go through the printing process. And we'll start all the way from square one of how do I figure out what I want to print, and then move into how do I get it ready to print, and finally, what do I need to worry about when I print it. So I think at the beginning of the day here, we did a show of hands who has or has not used a 3D printer, and we had like half and half. Is that about right? So for you that are new to 3D printing, what are you guys hoping to get out of it today? Anything specific?
Just learn the basics of it, how you use it.
Okay.
I mean, how we can apply it on maybe a smaller scale here.
And are you guys focused on applications, you know, that apply to your day job or for hobbies or all of the above?
I think probably all the above. Maybe the hobbies, just learn it, and get more experience with it. Maybe apply it to jobs here, whether it be on your craft, supporting the craft, just help us.
Okay. Sounds great. Well, I think we can hit on some topics that are relevant for all of those disciplines, and you know, we'll talk about how AM ultimately, 3D printing is ultimately just another tool in the toolbox, but it's a very versatile tool. So, and I know some of the feedback we got yesterday was that kind of getting into the actual hands-on, what to worry about, what to tweak to get a successful print. That is something that you guys in the online audience value. So we'll try to bias a little more time to that today than we did yesterday. So starting off briefly with the history of additive manufacturing. And so additive manufacturing is actually pretty darn old at this point. It dates back to the early 80s. And the first developed technology was what we call stereolithography, or SLA. And so you guys may have seen SLA in the form of a resin-based printer. So right here in the lab, you have a Formlabs Form 2. Is that right, Jed? Yes. Yeah. So that is an SLA printer, and that's how the whole thing started. The first patent was issued in 1986. So, you know, we're still talking over 30 years ago. And then they moved into a different technology, which is called selective laser sintering. And ultimately that evolved very quickly into an offshoot called fused deposition modeling, which forms the backbone of your consumer grade 3D printers that most people are familiar with. So this stuff's been around for a long time, but it's amazing because it is still evolving very, very quickly. And even in the last, 5 years, I mean, you could call it a decade, but a decade ago, printers like this were not accessible to consumers and probably out of the reach of small groups like this one. And now, if you have $200, you can get clean prints. And so it's come a very, very long distance. And so what's actually happening is, in the process of additive manufacturing, you're taking computer-generated designs. So you have a design that lives in software, and you are what we call slicing that file. So in order to take a part that's represented on your screen, almost all additive manufacturing technologies are going to build that part layer by layer. So we say 3D printing, but one of the things that we like to point out is really most printers are almost like 2.5D printers, because what they're doing is they're printing a 2-dimensional slice and then just repeating that over and over and changing each slice to ultimately arrive at your 3D shape. So in between the CAD file and the actual print, you have what's referred to as a slicer. And so that's what chops up your model into layers and puts it into a format that the machine can understand. And then it's also really important to point out that just because your printer is done does not necessarily mean that your part is done. And so there's a bunch of things that you need to worry about in post-processing, depending on what you're trying to do with that part. And just to cover a few pieces of terminology that you'll probably hear me use today, this is just to get past the basics. So we talked about SLA, which is a liquid-based process. And then the other side of that coin are solid-based processes. So things like joining and fusing, and that's where that selective laser sintering comes in, because you're using a solid feedstock or substrate in the form of, say, a powder, and fusing that together. We talked about what slicing means, what 3D printing means. You might hear me talk about service bureaus, and so that's really when you're relying on an external organization to supply additive manufacturing resources that we might not have here in this lab. So for example, we work quite a bit directly with Stratasys, or there's companies like Shapeways out there where if we can't print something in-house, we'll call them, they can do it. And within the DoD, you see that happening more and more often on a, say, a depot level, a maintenance depot level. So the Air Force, NAVAIR, the Marines are all investing pretty heavily in a logistics chain where you have access to really heavy duty industrial strength. So we talked about fused deposition modeling. Another technology that you'll hear me refer to is powder bed fusion, and we'll talk about that in more detail. There are several varieties. There's a laser-based process that is used to print metal parts, and then you can also see that technology for polymer printing, plastic printing as well. And then there's actually another technology called material jetting or binder jetting that chemically binds a powder together with heat and different solvents, and we'll talk about that. Oh, but one more thing I should mention. So wire arc additive manufacturing, you can think of that basically as a robotic weld, and we'll see an example of that. It's used to create large parts quickly. And when I say photopolymer, I'm referring to the type of material that's used as a feedstock in your resin printer. So it's a photosensitive resin that's cured when it's exposed to either laser or some kind of UV light. So starting with stereolithography, just a little bit on how it works. So if you look at that, if you take a look at that printer in the other room, what you have is a vat of that photopolymer in liquid form, and there's a movable bed, and then a laser on top that's going to aim down at the bed. So what happens is your build plate sits right at the top of the liquid. The laser head is going to move around and selectively cure that liquid into a solid to create your first layer. And then the build plate itself drops down. And as we talked about, you build your part layer by layer. And so you can see a finished part over here has already been taken out of the vat. But that's what's happening as you go down into your resin tank. And the cool thing about SLA, we'll talk a little bit about pros and cons of each of these technologies, but why would I want to use SLA over one of these that I probably going to see more of? Well, one advantage that we'll point out is that you can make very finely detailed features. And so this image right here, these two objects are on the order of nanometers in size. So this little windmill is about the width of a human hair. And so it's really a process that cannot be repeated even through any traditional manufacturing method, and that can make it very powerful. So talking more generally in terms of pros and cons, that feature size, that resolution is a primary pro. You can also use, so one example where that comes into play is, say I want to make a mold to produce parts through a more traditional casting method, right? I can use SLA to give me extremely nice surface finish and get those dimensions right on to create my negative for that mold. A challenge with SLA is that the materials are usually not as dimensionally stable and not as resistant to the elements as you might get with some other technologies. So this guy is made through an SLA process right here. It's a little bit tough to see, but so this was my boss, Jonathan, who was here yesterday. This has been sitting on his desk for a couple of years. And if you look, these screw bosses used to be parallel to each other, and this whole piece actually was curved. And just by sitting on his desk, it's actually crept to the point where it's almost flat. And so that's pretty typical of an SLA part. The other thing is that they are not particularly resistant to UV exposure. And so this is an example of an SLA produced piece where you can actually see the color difference. Again, just from sitting on a desk, probably catching maybe 30 minutes of sunlight a day. And the exterior portion that's seen that light has started to degrade a little bit. So it's something to keep in mind. So next up, we have FDM, fused deposition modeling. And again, this is by far going to be your most common, most accessible form of 3D printing. This is kind of what everyone's talking about when they colloquially refer to it. And it's the same idea. You're still building up a part layer by layer, but instead of doing it in a photosensitive liquid, you are taking solid material, fed through a spool right here. That material goes into a hot end, which melts the material, pushes it through a nozzle, and then deposits the melt in a thin line on your build plate here. And so you can actually see FDM printers that work both ways. Either the build plate will drop, just like the resin printer, or in this particular case, you have your what's called your hot end or extruder head, depending on where the extruder is located, will move up. And in some cases, like on this picture, you can have multiple materials in play at once. And so typically what you'll see is either two different colors or one of the more common applications, you have your primary material that you're building your part out of, and then there'll be another hot end and head that extrudes a support material that can be dissolved away later. And we'll get into why supports are necessary in a little bit. And so just something that I want to point out is this representation up on the upper right. And so this is basically a picture of a single slice or layer within your part. And you can see that the typical way that an FDM printer is going to build up a layer is by splitting it into a boundary or wall, and then doing what we call the infill, which is everything inside of that wall. And so this slice is showing more than likely an exterior visible surface because it's filling in the entire interior of that slice, right? But by default, 3D printers are going to try to use as little material as possible. And so if this were an interior layer, it would actually fill this in with a much sparser pattern. You almost never print fully solid FDM parts. And you can see here, this is an example of a part where we stopped the print midway through, and you can see that infill pattern. This is actually a fairly dense infill pattern. This guy is stiff, but you can vary that parameter depending on whether you want to save material, save time, save cost and weight, or if you need the part to perform in a structural setting, you might want to beef it up. Yes?
Is there specific patterns that are stronger than others for skills?
So there can be, and we can talk about that a little more in the demonstration today when we get into Cure, but yeah, there are a variety of infill patterns that you can choose. The most common is going to be what they call a linear pattern, which is you sort of make a series of crisscrosses within the part. But more recently, there's been adoption of some other patterns that can be really effective. So for one example is a gyroid pattern. Yep, and it kind of creates wavy three-dimensional lines. And what that does is it gives you strength in all three dimensions rather than kind of trending just in the vertical axis. That's a great question, thank you. And yeah, I should mention, you know, I want this to be discussion based. So if you guys have any questions, please feel free to stop me. So we talked about our primary components. It's good to know, you know, just the major elements of the equipment that we're using. One thing I'll point out is that you'll see two primary variants of FDM printer where, well, in addition to whether the bed moves or the head moves, that's one way they can vary. The other is that on this particular example, we have the extruder and the hot end all in one piece. That's called a direct drive printer. On this printer here, you can see this is a Bowden tube printer. And what that means is there's a tube, the extruder that actually pulls the filament along is over here. It doesn't go anywhere. And then there's a tube called the Bowden tube that connects it to the hot end. They both work pretty much the same way. They can have some slight advantages depending on the material and the setup, which we can maybe get into a little later, but that's what you'll see in use. So why should I use FDM? First of all, as we said, it's incredibly common. There's a ton of materials available, particularly in the polymer world. It's very accessible and it's very well understood at this point. So, you know, it's the kind of deal where if you want to know, if you want to improve your prints and you have a question about something and you search for it on YouTube, you're going to get 100 different videos that'll probably, hopefully give you a reasonable answer. And it's inexpensive too. So it's very easy to get into. The challenges are that material properties can be a little bit problematic. And you see that word anisotropic. We'll talk about that a little bit later. Basically what that means is that your material properties on an FDM part can vary with direction. You're generally limited to thermoplastic, so there are some specialty applications where there might not be a printable material that you can plug into one of these. And your dimensional quality can vary. I mean, you know, you have a wide range of printing options in terms of equipment, but on some of the lower end printers, you often are going to have to trade some fiddling and dialing in to get a really good looking part. Whereas some other technologies like SLA, it's a little more plug and play. Like what you see on screen is what you're going to get. So this is another major category that you're not going to see here at the lab, but I think it's important to know because it is getting a ton of attention at a higher level in the logistics and sustainment chain. So powder bed fusion, again, we're building layer by layer. In this particular tool chain, what we have is a feed chamber that's filled with a powder feedstock. Now that can be polymer powder, that can be metal powder. And then you have a build chamber, and basically the build chamber starts at the top, and you have what's called a roller and a scraper, and it scrapes a thin layer of powder across your build platform. And then you have a laser head that selectively moves and either sinters, or in the case of metal, actually melts the material together where you want that part to solidify. Build chamber drops down, feed chamber drops up, you roll and scrape a new layer, so on and so forth.
That sounds like that would be the longest duration.
Yes, you're absolutely right.
Let's come back to the new layer every single time.
Yep. And so, yeah, you run into some interesting constraints with PBF or powder-based fusion. Build times tend to be longer. The cool thing about PBF is that your build time is really tied only to your Z height. So because you have to scrape that layer every time, it takes a fixed amount of time the higher you go, but you can pack a whole bunch of parts into that build volume, and the parts don't have to be attached. Well, I'll say this, that sometimes they don't have to be attached to the build platform. So you could potentially stick 300 of widget A in my square build and build them all at once. And that's where you start to see some advantages. Yeah. And so this gets really interesting from a technology standpoint, because there's a lot going on as you dive deep and take a close look at this process. So, you know, what's happening is, in the case of, let's say, metal powder-based printing, your feedstock is this very fine, very tightly manufactured metal powder, and they try to make it as spherical as possible so that you don't get any abnormalities. And so here's your unsintered or unmelted powder, and the laser beam's moving across it, and it's melting that material. And then after it passes, the material solidifies. You get internal stresses, you get some shrinkage. So there's an incredible amount of material science that's happening during this process, and it's still very much an active area of research to figure out how to get the best results from this. And so, in fact, some of what we do and what our peer institutions do are building things like simulation models to show you exactly what's going on at a microstructure level of that material as it's being printed. So pros and cons of PBF. Oh, yeah.
So what kind of, or how uniform does the material really be for the powder? Kind of imagining people putting soda cans into a grinder and getting a bunch of powder that way.
Yeah, so for good results, it needs to be pretty tightly controlled. You may have seen, like, there's actually equipment and people out there who make their own FDM filament. That's not really a thing that happens for powder-based fusion. It has to be done in an industrial setting. There is some variation, but there's a pretty clear relationship where the more uniform your powder is, the better results you get out the back end. And so one of the things you can do with PBF is you can actually recycle your unused powder. But that, again, that's another active area of research, is how much can you recycle it? Because each time, like, especially around the boundaries of your part, as that laser's moving, you get some stuff that maybe kind of sort of melted, but not really. And then you have to worry about, is that now being fed back into my feedstock if I use that powder again?
Imagine something that just like cut the contents of the dump produces something.
Sure. Yeah, I don't think we're there yet, but it would be great. So for powder bed fusion, primary advantages are that you can get some very structurally sound and very good looking parts. So I have a couple examples here. This is a bracket that's printed out of, it's called MS1. It's a margin steel. So it's a very strong, very hard steel, probably similar to something in the chromoly family. And this part is, so when you print in PBF, you typically print solid. because there's no way to get that powder back out unless there's a hole to drain it from. So this is above 99.9% dense when compared to something machined out of billet. So it's largely indistinguishable from the real deal. And you guys are, I won't pass all these around because of COVID, but you guys are welcome to come touch these when we're on a break. Now, the challenges are that you have a lot of thermal stress being generated during that process. So warping can be a big deal. It can show up in the resulting material properties as well in terms of its strength. And the process is still pretty expensive. So definitely for metal, this is not really accessible to a consumer yet. It needs, again, you need sort of a more tightly controlled facility. If you're printing in aluminum or titanium, which is going to happen a lot in the aviation world, those materials are reactive in powder form, so they like to either light on fire or explode, and so you need precautions around that. But it's a big deal, and so actually right down the street from here, there's the ATTC, which I'm not going to remember that acronym, Jay, but
Advanced Technology and Training.
Okay, yeah, so they have a bunch of metal printers, and they're doing a bunch of work for the Air Force trying to figure out the best way that this can be incorporated on actual aircraft. And I'll mention briefly material jetting. This is not likely something that you're going to run into, but it's a lot like SLA, but it uses chemical or photosensitive binders. So it actually works a lot like an inkjet printer. You have a head that moves across the powder layer, deposits those binders, as we call them, those photo or heat sensitive chemicals onto the powder, and then a heat lamp comes across, heats them up, and it fuses them together. And you can do some really neat stuff with this in terms of printing in either multiple colors or multiple materials. It's used quite a bit in the medical world, actually, as you can see there. And finally, we mentioned wire arc AM. Again, robotic welder, it's not precision. You're not going to get something that looks pretty, but it is fast. And so there are use cases where, if you have a reasonably large part, and your alternative would have been machining it out of a big block of material, you can do this to get something that we call near net shape. And so it's ugly, but it's close to the final shape, and then you can just machine around the edges to clean it up rather than wasting a lot of raw feedstock. So what can, all right, you guys have heard about how all this stuff gets done. What can you do with it? So one thing that we use day in and day out at GTRI is for tooling and assembly aids. So anytime that we need to hold something or fix something, or if we're trying to put something together that has custom geometry, this is a great tool because it's so easy to create something one-off and keep that tool fairly low cost. You can use it for short-term repairs. So, if you have a vehicle that's stranded somewhere and you just need to get it back out of the field, back to base, that's something that's being looked at in a lot of applications for kind of rescue and emergency use. You can use it for things like part consolidation. So this is another metal printing example of a fairly basic bracket. It's nothing special, but the interesting thing about this part is that it started off life as a 3-piece weldment. So it had this flat plated black welded to this plate here, and then this curved piece was number 3. And so they were able to print this and turn it all into a single part. And you can do that on an even larger scale and save yourself some time and labor that way. And finally, just general prototyping. So I'd say, a lot of what I do and what my group does in our laboratories, we do prototype systems and kind of first article systems that might be destined to hand off to another larger manufacturer like a Lockheed later on down the line, right? And so when we're in the prototyping stage, I cannot remember a recent project where we didn't have parts being 3D printed to get form, fit, and sometimes function just because it's so quick to iterate. Now, like we said, AM is a tool in the toolbox, and when do you want to be careful? So I think one area to be careful is for parts that are under high stress or high cyclical loading. And we'll get into the details on why, but you know, it's important to understand design intent, and often your material properties for something that are printed are not necessarily the same as the material properties for something that is made out of the same material in a different process. And so you have to be mindful of that. And then high volume production, what did Jonathan say yesterday? He said that, you know, they used to call 3D printing rapid prototyping equipment, but the term rapid is maybe a little bit of a misnomer. So it's rapid in the sense that I can pump out multiple design iterations quickly, but the actual production itself does not really hold a candle, at least not yet, to a lot of traditional manufacturing needs. And so there are limited applications if you need 1,000 of something or 10,000, where you would want to look at now they are out there. One industry that got mentioned yesterday was the medical industry, particularly dentistry, uses additive manufacturing at a pretty high volume. So Invisalign braces, they're doing things with stuff like crowns that get 3D printed, but it's limited. So these are some examples of when I would want to use polymer printing. So again, we have rapid response manufacturing, and this is where the lines between prototyping and mass manufacture are a little bit blended, right? So the presentation earlier talked about all the COVID PPE efforts, and if you spool a bunch of 3D printers up, you can get, you know, hundreds, maybe a couple thousand parts a day out of a given regional area, and that's awesome. Or it can be a stepping stone to larger quantities produced via a different method. We talked about tooling and prototyping, and then there's some really interesting, unique devices that you can get via a polymer process. And so a big chunk of the research that we do at my facility, it revolves around RF systems, so radars, communication equipment, and we use 3D printing to get some unique antenna designs and things like that. Metal AM really comes into its own when you're talking about things like that part consolidation. So if I want to replace a weldment, you can get incredibly complex with the designs that you can print. And so some examples are popping up in aviation. So there are examples of companies like GE who are playing with 3D printed turbine blades and other components that are going in those aircraft engines. It's pretty neat. And then also, we mentioned the logistics chain, and that's another emerging area where you're seeing the various DoD branches figure out how to make what they call OEM equivalent parts to put on vehicles. And there are numerous examples of that. And we'll talk about a couple of those later. Now, just to touch on kind of the special topic of parts that are going to be used in production. As you guys know, you're all airmen and women. So things that get approved for the flight line or on an aircraft are a really big deal, right? And so there's a ton of work that gets put into figuring out whether a part is okay to use in a production system, and that is still a very evolving area. So this is one example that we like to use on the upper right here. That's a cap that goes over a fire extinguisher or a fire suppression system. And so this was something that the military was looking at because it was a part they had a shortage for. Seemed like a great idea, right? It's super simple. They can crank them out and be done. Well, there are potential safety implications even to something that simple, because what if your dimensional tolerance gets thrown off, the part prints a little tight, and you have a technician that's going to put this on, they don't know anything about it, and so, oh, it's a little tight, I'm just going to tap it on there with a mallet. Well, what if your fire suppression system is not going to activate properly? So that's why, and I know, we get a lot of pushback from people on the ground or on the front lines to, hey, I printed a test piece, it works, I just want to use it. And we definitely understand that, but it's a balancing act between that desire and having, say, either the flight office or program office go through the necessary level of rigor. And you can see another example down here. So this was an exercise that NavAir did. They printed an engine linkage for the V-22 Osprey. Obviously a flight critical part. In fact, I think this was the first example of a flight critical component that was deployed. But if you look at this build plate, so this is a powder bed fusion build plate printed in metal. And you can see here, that's the linkage. They printed, I can see 2 copies. I don't know, maybe there's another 2 on the other side. Everything else you see on that build plate is a test coupon. So they printed probably about 30 test coupons that they then pulled apart, placed under fatigue, simulated the actual loading conditions, just to make sure that those, 3, maybe 4 parts that they produced and were actually going to use met the design goals. And that'll continue to evolve as we understand, the technology better, but that's where it's at right now. If this is something you're interested in, because there is a lot of ongoing work within the Air Force as well, you can find out more about like what's being done as far as approval guidance, best practices, and there's some stuff out there that kind of every branch is doing their own thing. And part of what we do is try to get everybody talking to each other to leverage all the good work that's happening. But you can find things from the Marines, you can find things from NavAir, and from the Air Force as well.
How recent was that part for the V-22?
I want to say that was in 2018, if I remember correctly. So NavAir has done a pretty good job of getting out there and investing in the flight critical process. But it's still very much on like a very carefully controlled, one-off basis. Where they're doing limited deployments, they can track it closely. I think you are starting to see both on their end and on the Air Force end, you're starting to see non-flight critical parts that are being approved for slightly larger rate production. So there's some interior piece that they're just having a ton of trouble sourcing. That's starting to get put on actual airplanes for an extended period of time. And if anyone is a real nerd like I am and you want to dive deeper on this stuff, there's some good academic materials, and this is one book that we use as a resource to get into the finer details of how all these technologies work. So yeah, that is kind of the conclusion of an AM overview. Did you guys want to take a quick?
Yeah, we'll give Kyle a break here. We'll take a 5-minute recess, I suppose, and we'll come back in 5 minutes. Stretch our legs.
Does anyone?
welcome back. Now Kyle's going to finish the second half of this talk about how you actually use some of these additive manufacturing tools to create things.
All right, let's get into it. So what we're going to cover here, we'll start with how do you produce additive manufacturing components. And so this is, any of the things that we're talking about today, you can dive as deep down the rabbit hole as you want. And I would encourage you to do so because there's just a wealth of information out there. Whether if you're a video person, YouTube is filled with this stuff. If you're not a video person, there's really good blogs and websites that focus on articles. But we just want to give you a little bit of a framework to think about it as you move forward. And so we'll talk about part selection, figuring out what I want to print. We'll talk a little bit about reverse engineering, which gets into aspects of, say, the 3D scanning that you guys got exposed to earlier today. Then we'll move into what do I do with the geometry once I have it, and that's manipulating it through computer-aided design in your CAD program. And we'll also talk about design for additive manufacturing, and it's a pretty broad topic, but it deals with changes that you might have to make from an original part to get it ready to print, because you may not print the exact same thing that you ultimately want to end up with. And we'll talk about why. And then finally, we'll spend some time on the additive manufacturing process flow. So what do I need to do before the print, called pre-processing? What do I need to worry about during the actual printing process itself? And then what do I need to worry about afterwards? All right, so how do I think about part selection? And when we think about this problem, we like to split it up into two major overarching questions. And this question of what do I 3D print is actually a huge business. And so part of the sponsored work that GTRI does for the military is developing technologies that allow us to go through entire vehicle platforms and make recommendations, automated recommendations on what can and should be 3D printed. So as they work towards trying to figure out how to create real parts that can replace original parts on a vehicle, say for an aging platform, they need to know how to make that decision without having an engineer pore over every single component for multiple hours. So this is a big question that's being asked at all levels, but it's a good one to ask for yourselves too. And so the first question is, can I 3D print? And what that question boils down to is, do I have the technical capability to recreate what I have in my mind or what I have in front of me that I want a copy of with the equipment that I have on here? And so you have to ask yourself, well, what is the OEM part, or what is the original component doing? What were its loading requirements? How long was it supposed to last? And then does my printer have the ability to recreate those characteristics? So you can start with the basics, like, is it actually going to fit in the build volume? How close of a material match do I have? Because you often, most of the time, for FDM, for example, your filament options are relatively limited. You have a set of filament materials, right? And those may or may not be what your part or your idea is supposed to be created out of. So you have to look at that. And then the second question, should I 3D print it? That's when you start to go beyond the technical aspects and asking yourself, well, given other contexts, is this the right way to go about it? Because what we like to preach at GTRI is that, and I mentioned this earlier, 3D printing is another tool in the toolbox. And so it's a very accessible tool, it's a very versatile tool, but it's not always the right answer. And you'll see, a lot of 3D printing proponents want it to be the end all be all. It's an incredible technology, but it can't replace everything. And so this is where things like asking yourself, what's the risk level of doing this? And so, for parts that go on an aircraft or for anything flight critical, that risk level automatically is in a completely different category. And you have to do a lot of extra homework. What's the relative cost? Again, this is great because it's here and I have access to it, whereas I might not have access to, say, a mill. But for certain parts, it may actually be cheaper to machine it or to injection mold it, and and it depends on when I need it, what the quantity is, all of those questions. And that plays into, you know, what are the alternative ways that I have to get what I want? So we've talked a little bit about this process. You go from geometry, programming the machine, to actually monitoring the process itself. And so we'll talk about CAD in a moment. And then we've talked about the slicer. And so that slicer, beyond slicing it up into different layers, it's going to issue your machine a very specific set of instructions for what it needs to be doing. So what's going on under the hood of this guy right here? This machine does not have a ton of intelligence built in, right? It's going to take a set of instructions that we call G-code, and all that G-code is just a bunch of lines that have directions like go to point 0, move 3 millimeters to the right? The bed needs to move fraction of a millimeter down, so on and so forth. So the machine is not actually watching what's going on. It's just reading that list and doing what it's supposed to. And that's why, you know, if you guys have seen 3D prints before, you can end up with what we call failed prints, where at some point in the process, something went haywire and you end up with what's called spaghetti, where it's just a pile of crusted filament, right? And this is an example that the printer was able to recover from. Sometimes it can't. Sometimes you come back in the morning and it's just a ball of crap. But there's very little process monitoring that's happening on a consumer grade printer like this. Now that's changing, and on some devices that you pay more for, they have more intelligence, more sensing, what have you. You can actually tell what's going on. But those are the basics. And then again, like I said, we'll talk about what happens after the print, and that falls into the category of post-processing. So you heard from the Spark Lab about 3D scan. There are a lot of tools to do that. And I know there was a question, was it an online question about how you would get into 3D scanning yourself. So one thing I will mention, in addition to the excellent overview that those guys gave, is if you want to dive into this on an individual level, you can look up the term photogrammetry. And so what that means is it's the art of measuring things with visual data. But most of the production 3D scanners that you see are going to use lasers typically, and they bounce light off an object, give you that point cloud that then becomes your computer geometry. Well, there's a lot of open source projects out there that utilize nothing more than a camera, and that camera can be a good camera like that one in the back of the room. It can also be your iPhone camera. So if anyone is intrigued by that, there's a bunch of options. One project out there in particular is called OpenScan, and it's a combination of the software and parts that you can 3D print yourself to make a little turntable, and it relies on your smartphone as the image source. And you can do some 3D scanning on your own. Now, things that you want to consider if you're reverse engineering something, and the Spark Lab mentioned this, but you know, what is your tolerance and your error propagation? So no scan is going to be perfect, and depending on lighting conditions or the equipment that you're using, the surface that ends up getting scanned might not exactly represent the surface that you're looking at or the part that you're trying to make, right? And so you just need to be mindful. Again, if it's just something you're doing for fun, maybe that's a don't care. If it's a production part that you're trying to make a copy of, you need to perhaps quantify that. And then the other thing to worry about with reverse engineering, in particular scanning, what does the interior of the part look like? So if I'm trying to scan something like this, that's going to be a tall order because there's so many internal cavities in here that it's going to be difficult for me to penetrate that with the scanner. And so I really am probably going to need an additional option if I want to recreate this code. So once you have your geometry, typically whatever software comes with a scanner, or if you're starting with a model that you got from somewhere else, you know, most of those programs will export it to a format that can be opened and manipulated in a CAD package. And this is where, if you're creating custom objects, you're going to be spending a lot of time. There are a bunch of options to do computer-aided design. A lot of them are free, or a lot of them are not. And I would encourage you guys just to explore what's out there, because there are several different workflows that manufacturing so you can get exposed to, and often it just comes down to a matter of personal preference. So, for example, Tinkercad is a free piece of software that's extremely basic, but it's easy to get up and running. Whereas you have offerings from, say, Autodesk Fusion 360 that also can be free if you have. I think they give educational discounts, maybe military discounts as well. But it's got a steeper learning curve. So it really just depends on what your objectives are. And then there's a world of kind of professional software packages like SolidWorks, PTC Creo, and those are for doing things like complex surfaces, assembly management, and if you want to do any simulation work. So if you are designing a piece of something that has loads applied to it, you want to understand what that loading is going to do, you'll have to find, or you may want to find something that has a simulation package so that you can model that before actually putting it in a real world situation. And the final thing that I'll mention is that there are a ton of ways to get pre-existing CAD geometry out there. So for anybody who's done 3D printing, you probably are familiar with Thingiverse. It's an online platform where people host their models. There are other options that are maybe not as big, but have features that Thingiverse doesn't have, and also just give you different sources to find what you're looking for. So I won't go over all of these, but it's definitely worth checking out a broad range if you're looking for something, because often you can be really surprised at what people have A, spent a long time building a model of, and B, putting it online for free. So it's always worth a try, at least to get a starting point. And then finally, it's important to think about how 3D printing can help you beyond creating the object that you want to end up with. And so this, I think, is one of the biggest advantages of having a 3D printer, is that it can help you even if you can't print the thing that you want. There's usually a way to make another manufacturing process easier or cheaper or faster with a 3D printer at your disposal. So a couple examples here, you can see on the upper right, this is an example of a silicone molding process. So what they did was they 3D printed an object, then they cast a mold around it, and then they use that mold to make more copies of something else. This is great if you're working with, for example, like this looks like a grip. So if it's a material that's too flexible to be printed, that's a great way to get yourself a copy. Applications like vacuum forming molds are a good one. That's something that we've used in our lab. These two are examples of 3D printed press forming dies. So it's pretty incredible. These are both polymer tooling that's being used to bend sheet aluminum. And I've seen actually some even cooler examples of this for people doing things like car restoration work, where they're printing a die and then using like a home shop press to get a custom body panel for their old pickup truck, rather than taking the rusted out shell of whatever's left and trying to build it up with enough Bondo to get by and paint. So there's really no limit to what you can do as far as tooling. All right, so moving on down the line. Now I have geometry for whatever I want to print, whether it's a part or a pre-existing model or a tool. What do I need to do next? And so this is where design for additive manufacturing comes in. And this, again, boils down to two primary questions. The first one is, how will my part differ from the one that I'm trying to replace? And so that comes down to You know, are there going to be material property differences? Is this thing going to have a different lifespan because I'm printing it? And then the second question that I need to ask is, how can I take advantage of the unique capabilities of additive manufacturing? And so diving a little more into the first topic, this is an example of work that we did with the Marines. And so hard to get a sense of scale from these pictures, but what you're looking at in this picture right here, that's a 14-inch diameter pulley. It goes on a 50-ton crane, probably, I don't know, about an inch thick. And there's a wire rope that sits in the cross section in the middle of the pulley there. You can see it rigged up for load testing in the upper right. And so we worked with them to figure out exactly how to print this. And one of the things that we had to consider was that the metal printer that we were using had certain limitations to the surface finish that you get. But the part, the OEM part, needed a very fine level of finish and a very fine level of tolerance so that you didn't introduce undue wear on that wire rope that's handling all your loads, right? So rather than just directly recreating the part geometry, what we did was we added material where this red line is, and then we machined it back off in post-processing to get it back to the drawings. And this was another area where we ended up beefing up the material and then doing some removal to get that surface finish. There are other things that you might want to consider changing in order to make it more conducive to additive manufacturing. So things like overhangs or horizontal holes. So if you have overhangs and you don't have a means of supporting it from underneath, your print quality is going to deteriorate. And you can look at these example pieces. This is an example of a 3D printer test piece. And so what this is, a bunch of different features, and each one is designed to specifically calibrate an aspect of your printing. And so if you see this little curved bridge here, what that's testing is increasing overhang. And if you look underneath, you can see that the surface finish degrades as my angle gets shallower and shallower. And that's because the printer is having trouble depositing the material with nothing underneath it. And so it's depositing it, it's melted, right? But if it's melted, it's a liquid, it wants to sag. And so as I get shallower and shallower, it's going to sag more and more to the point where if you see a printer that's not dialed in well, it'll actually start falling away from the piece entirely. And that's a sign that there's probably not a good way to print that without adding support material. And in some cases, you might actually change either your part orientation or the way that the part is designed, if that's allowable, to account for limitations of your printer, such as that. And then the cool stuff, so the cool part of DFAM is stuff like this. So we can do some incredible things with 3D printers that cannot be done otherwise. One of them is topology optimization. And what that means is basically taking a part design that probably was designed with the limitations of its original process in mind and just getting it down to the bare minimum of whatever it needs to do its job. And so here's an example of an aircraft bracket. And this is the original right here. And I don't know whether that particular piece was machined or cast, but you know, they did this little scoop design here because you were using an end mill maybe, or they had to get it out of a mold. But when you go to 3D printing, you can say, well, what's the minimum amount of material that I need to carry the design with? And so you end up with really crazy looking, almost organic structures like this. Maybe it's a lattice structure, or maybe you just removed a bunch of material. And I mean, I don't know, maybe you could machine that. But you need a 5-axis mill and it'd be incredibly expensive. But to the 3D printer, it makes no difference. And sometimes you can get into structures that are completely impossible to make through any other means. You can do things with multiple materials, which is really cool. You can do things like part consolidation. We talked about that bracket example where you might have previously had a weldment. This is an example of that. So this is a kind of a sheet metal stack up with 8 different components. And when they end up 3D printing it, now it's down to 1 part. And it's also probably lighter than the original as well. And then what we call multi-scale structures is just that your deposition rate for a 3D printer doesn't really change. Like you set your feed rate at the beginning of the print, and it lays down material at that rate, and it doesn't matter what the geometry that it's building is. It's going to go at the same speed. And so you can create stuff that is right down to the limits of the machine resolution, all the way up to the full scale of its build volume, and you don't have to change your tooling. You don't really have to do anything differently. Where you might with another process, say you're working with a mill, in order to achieve those ends of the spectrum, you're going to be swapping out tooling. You're going to be changing your fixturing, all that good stuff. So once I'm happy with my CAD model and the way it's designed and prepped to be printed, I need to get it to the printer. And so this is where that pre-processing step comes in. Is everyone here familiar with STL files? Anybody not familiar with STL files? Okay, so what you need to do to get your CAD model to a state that's ready to be printed, you have to get into a neutral file format first, because every CAD program has its own specific way of storing information, and that way is not necessarily something that the 3D printer can understand. And so an STL file is a neutral file format. It takes your CAD geometry, and what it does is it represents that geometry with a series of points that are all connected together to form triangular facets. So if I take an example here, let's say this guy right here. So if I were to make this into an STL file, what it would do is it defines a resolution which controls the number of points, and it would split these curves up into a series of points, and that's all the information that gets stored. So it's pretty simple, but then it's in a format that can be understood by my slicing program, which is the next stage of the process. Now, STL files are ubiquitous. So if you go on Thingiverse and you find something that you want to print and download it, that's the format that you're probably going to see. It's also a very old file format, and because of that, it has some disadvantages. So it was invented in 1987, like most things that were invented that long ago. It's probably a little bit behind the times. I shouldn't say that too loud because I was born in '86, but there are more modern alternatives. And so as you guys start getting more familiar with the workflow, I would encourage you to get familiar with them as well. So the strongest alternative right now is called the 3D manufacturing format, or 3MF is the file extension you'll see. And most slicing programs support 3MF natively in addition to STL. It's a very similar technology. You're still using a point cloud to represent all your features, but it has some specific improvements that are really good for additive manufacturing. So it can represent curves in between the points as opposed to just straight lines. It can store color and texture data. So it's just kind of a better way of doing business. You'll see both, but it's good to know what they are and what they mean. A couple of things to pay attention to. So this is a step that you'll have to perform if you have a CAD model. You have to export it or save it as an STL. And when you do that, you have to pay attention. The most important thing is resolution. And so that's the distance between these nodes and ultimately the size of your triangular facets. And that's going to make all the difference in the world, because if I take an extremely complex part and I set my resolution too low, when I print this, I'm going to see all the individual triangles, especially in places where there are tight curves or little recesses. So you have to make sure that your finished STL or 3MF has an appropriate resolution and looks like what you want to achieve. It's a balancing act, because as you crank up the resolution, your file size is going to increase, but usually that's not a huge issue. You can also have some issues with STL generation, particularly with scan geometry. So every once in a while you'll run into a problem where there's like a hole in that surface, or just some other weird issue with the mesh. That's not really an introductory topic, but there are ways to deal with that. And there are some software packages that can help you out. In fact, I think Yeah, so we'll cover one of them on this slide. So when you have your STL or your 3MF file, the next step is going to be slicing. And we talked about slicing being parsing that information into the format that's actually going to get printed and the instructions that the printer understands. There's just like with CAD, there's a variety of ways to do this. There are programs like MeshMixer. That's one that's designed to manipulate things in the STL format. So like I was saying, if you need to repair an STL or a mesh, MeshMixer is an option. Cura and Slicer are both actual slicing programs. They're both freely available. Cura is developed by Ultimaker, which is a 3D printing company, but it works for almost any printer. And in fact, that's what we use in our lab. That's what I'll show you guys today in just a minute. And it's a great program, so you really can't go wrong with that. But this is where you're going to control all of your print parameters. So often you'll have a set of defaults for the printer that you want to use, but then you can tweak any of them. So you can choose your infill type, both the pattern that we talked about earlier, as well as the density. You can change your feed rate, so how much filament the printer is going to squeeze through, and that can be used to solve issues with your build if you're having them. You can change the process temperatures, your travel rates, and how fast the head is going to move. You have pretty much control over anything that's actually adjustable. And we'll talk about why you would want to change that stuff. And then you also need to worry about support, which is something that we mentioned. And you have a couple different ways to do that as well. So there's two primary types of support. There's what we call tree structures, and that's where the slicing software itself actually uses some fancy algorithms to hold up these overhangs while using as little material as possible. It sort of ends up looking like these scraggly trees. It's interesting. It's still a little bit experimental in some cases, but it's worth trying. And then you also have lattice structures, which basically means that just like with infill, where it's going to create maybe a crisscross pattern or a gyroid pattern, it's just going to build up exactly the same type of pattern underneath overhang areas. And again, you can change the density, which is ultimately going to control how much material you use and how long it's going to take. But it's also going to support those overhangs more effectively. You can change the pattern too. So there's usually not a huge need to fiddle with this, but say for example a concentric pattern, it's a great option if you're trying to print, for example, a sphere, because it supports evenly rather than trying to use a more traditional lattice structure that's just orthogonal to itself. Yeah.
Is there any like general rule of thumb with supports? Like, you know, I've seen 45 degrees, and I've seen, hey, percentage density of support APUs. So is there any like kind of beginners, where should they start, and where should they kind of tweak up and down?
Yeah, that's a great question. So I would say, in my practical experience, that 45 degrees is a good rule of thumb to pay attention to. So if your angle is steeper than 45 degrees, if your printer is working relatively well, it's probably not something that it should have a ton of trouble with. If it's 45 degrees or shallower, then you just have to keep in mind that you may run into issues. Now, one of the great things you can do is for any printer that you're going to use, I would definitely recommend printing a test piece like this, because A, it's going to help you dial things in, but B, it's going to help you understand the capabilities of your printer. So this is something that I did on my printer at home, and it actually passed the overhang test pretty well. I'd say the only one that I'm really not happy with here on the underside surface finish is at 15 degrees. So I know that unless I really need high precision, there's a little bit of wonkiness going on at 20 on the edge. But if I don't need incredible precision, I'm probably okay without support on anything up to that 15 degree angle.
We can look at this one, which was done on this printer. This one actually did really well too, up to about 50. But then there's also things like, so it closely related to overhangs, what we call bridging, and that's creating completely unsupported structures. You can see here that the idea is that you want this horizontal slot in here, and it gets progressively longer. And so, like on this printer, I think this is about a centimeter, 10 millimeters, right? Did that perfectly fine. 20 millimeters, you can still see the gap, but it's starting to sag a little bit. 30 millimeters and up, now the filament is just starting to separate. And that would be another easy way. So now I know if I have features that are that size in width that have nothing underneath them, probably a good idea for me to add support. Yeah. Yeah, so support removal, it can be tricky. So the question was, if you're having trouble getting the support material off of your print, what do you do? And so that really, it depends on a couple of things. I'm assuming you're talking about when you're using single material printing, right? Yeah. Okay. Yeah, so if you only have a single extruder, if you use support, you have to use the same filament, and that means that your support has to be mechanically removed. Now, the slicing software will try to make that easy for you. So usually what it does, it'll build up these structures, but then it's a little bit hard to see, but like if you look closely right here, right where it touches that werewolf head, I don't know what it is, it actually reduces the cross-section down to be very small. So it's designed to almost break away. Usually that works okay. Sometimes it doesn't. So yeah, if you're having trouble removing it, I would say definitely try reducing the support density and seeing what you can get away with. I think Cura has a few settings as far as like what happens at that interface. You definitely should try tweaking those as well, because that could help it out. Sure. Okay, so just to show you guys what this process looks like, let me get on station here, and we'll just do a quick demonstration of this workflow in terms of slicing apart in Cura. And so when you open up Cura, this is broadly speaking what you're going to see. You'll actually see a blank build plate, and then what I've done already here is just gone to this file open and chosen my 3D printer test. And so what this will do is it places it on my build plate. It automatically tries to place it on the plate itself. Sometimes if your geometry is really complex, you'll have an issue where it'll slap it on the build plate and it either won't be touching or it'll be in an orientation that's clearly not printable. So what I can do is I can click on the part, and I should mention that what I've opened here is going to be one of those neutral file formats that we talked about. So this is either going to be an STL, 3MF. Cura supports a couple other things, like I think it supports OBJ files. It just depends on what you have. Those first two are going to be the most common. And so I'll bring it in, and so if I want to tweak it, I can move it around. This gives me along my primary axes. I can move it. I can try to move it off the build plate, and Cura says, no, you can't actually. And then I can do things like scale it, that big, or rotate it. So as I rotate it, you can see it again, it tries to put at least one edge on the build plate. But, obviously if I wanted to do this, I'm going to introduce some additional things to pay attention to, like do I need support underneath there? So what you really want to try to keep an eye on, what is my optimal build orientation? And usually that means minimizing the need for support or areas that are likely to want support. So once I have things where I want it, and if you right click too, there's some neat features. So like, let's say I want to make multiple copies of this. I can say multiply selected model, choose my number. I just want one more. All right, now I have two. Then I can go to arrange all models. And I don't know that this algorithm is super smart, but it tries to arrange things evenly. And I think it does pay a little bit of attention to where they are relative to the extruder head to try and minimize your build time. Now, some people go crazy with that. So like, you can see that the home position for my printer head is over here in this corner. And so it actually makes a difference. If I print something over here on my build plate, it's going to take longer in some cases for it to print than if I put it over here. Just because there are, and it depends on the printer, but some printers are going to want to home between various operations, and it can take longer for it to do that with stuff that's over on the build plate boundaries. I wouldn't worry too much about that, at least until you're comfortable with the basic process. So most of the time, you just sort of cluster things around the center. That works great. You want to make sure that Cura is set up for your particular printer. And so here you can see we have two monoprice printers that are already set as presets. I can either add a new printer. I don't think you guys have any network printers here, right? Yeah. So you go to add a non-network printer, and you can see they have all these manufacturers. Most of what's available on the market, you'll find presets here. And I can just say add. And then if I want to customize, I can also do that. And so I can go in here, and these are my machine settings. So this is where I think like really basic stuff like my build volume is set up. In general, you probably don't want to mess with these unless you have a specific reason for doing so. But it's there. And then next thing I'll do, I'll make sure that I choose my material. If I have multiple print heads, then I'll be able to choose a material for each. And then, yeah.
Yeah, material behind you, put it over there.
Oh, cool.
Yeah, there's all laid out there.
Yeah. So this is what your spool of FDM material looks like. This is almost always the format that you're going to see it in. Typically, it's sold in either 0.5 kilogram or 1 kilogram rolls. And if you go and look at any of the printers in the lab, you'll see it just gets installed on either a post or a roller and fed into that extruder. And this is, so a lot of consumer printers are going to be 1.75 millimeter diameter, and that's what this stuff is. There's also some thicker diameter filament. I think you can get 2.5, and then there's like 4.2, which is not as common. But 1.75 is what you'll see the most of. And it all, I mean, on the roll, it all kind of looks the same, but you'll see that every material has a label. And we're going to go over some details on individual materials and why you might use them in just a minute. So once I have my material chosen, over here is kind of the meat and potatoes of Cura. And these are all my print settings. And so by default, I have a number of predefined profiles. And these terms that you see in this drop-down menu are essentially quality levels. So fine, normal, draft, quality. And what those are doing, they're going to change a whole bunch of things at once. The most noticeable changes are going to be things like layer height, and that's actually what's highlighted here, that number after the name. So my normal print profile for this printer is a 0.15 millimeter layer height, and that's my step size in Z. So every time the extruder head moves up for a new layer, that's the distance that it's moving. It's also potentially going to change things like feed rate and how fast the head moves to give me a faster versus more accurate print. And so in my experience, I mean,
Cura does a pretty decent job, especially for PLA. And again, we'll talk materials. PLA is usually one of the easier materials to print. And I think for the most part, they get their settings pretty dialed in to where if nothing's wrong with your printer and it's set up and adjusted right, you should be able to get a usable print with the defaults. But particularly as you get more advanced and either using more esoteric materials or trying to do some crazy stuff with your geometry, that's when you might want to start tweaking things. And so just to go through some of that, we'll go through these categories. So again, quality is very much influenced by your layer height. Shell, so the shell category is basically how thick my wall is, which is that exterior layer or set of layers before the infill starts. So I can adjust how many layers of filament it's going to use for that wall. I can adjust it differently at the top and the bottom of the part versus the rest. I can do all sorts of stuff with that. And that's, again, it depends on what your application is. How strong do I need it to be? Am I going for something that, let's say I want something that is relatively water or airtight, I might want to increase that wall thickness just to give me a better chance of not having any porosity through those outer layers. Then I can look at infill. And so we talked about infill density. That's how much of the interior is going to be solid. You can go all the way from, actually, I don't know what would happen if you did 0% infill. Maybe it would just try to print a shell. But you can go all the way to 100, which is a solid part. It's pretty rare to see fully solid FDM parts. And what you'll notice is that once you get up above probably 30 or 40% infill, your build times get really so usually you ought to have a good reason if you are approaching a solid interior. So this is for my material. This is my print temperature. So PLA usually likes to sit right around 200 degrees Celsius. As you move into other materials, more structural materials, they're going to look for hotter. Actually, one thing I'll talk about that we didn't talk about yesterday is that with a Bowden tube printer, you have this plastic tube and it extends into the hot end. And it's actually, it gets pretty darn close to the nozzle that's being heated to your print temperature. And so this is just a quick safety consideration. If I'm printing something like, say, nylon or ABS, those require a print temperature that's close to a temperature where that Bowden tube material, which is usually PTFE, starts softening. And PTFE is one particular polymer that can actually release some pretty nasty stuff when it starts melting and off-gassing. So my advice there would just be that you can print some of those materials on these printers, but definitely do your homework in terms of what the print temperature needs to be versus what is safe for your particular setup. And so something like the Taz Lulzbot that's in the other room there, that's a direct drive printer, doesn't have this tube. And often those printers can handle much higher print temps because you're not worried about anything else, plastic in the vicinity. So here's my print speed. I mentioned this briefly in the presentation yesterday, but print speed is a huge determinant of print quality. And I'd say if I could give one piece of advice for adjusting or tweaking print parameters, it's that if you're having issues with a print, slow it down. Because it's amazing the amount of issues that I've seen get solved just by trying literally the same thing again and slowing down my feed rate or my print speed and just kind of letting that work some things out. So travel refers to when the print head is moving but not extruding material. So that's like, in fact, these little posts on top are designed as a test to test your travel parameters. And what you see here, so this one did a pretty good job. There's a few thin wisps of material in between those posts. But here it's much more pronounced. This is called stringing. And basically what's happening is that even though the extruder stops, so it prints this little piece and it's time to move on to the next post. The extruder stops forcing the filament through and the head moves over. But because things are melted and because there's some pressure built up, it's kind of like if you ever use like a caulk gun, right? Sometimes you stop squeezing the caulk gun and it's still coming out and you make a mess. It's the same idea. So the idea is to eliminate that, and the way that that's normally done is through something called retraction. And so what happens is when it needs to stop printing here and move over to the next piece, it actually pulls the filament back to relieve that pressure and stop any extra from oozing out. And so you can enable or disable retraction. In fact, if you, and this is kind of the condensed guide, and you see here, I have basic settings activated. If I enable all settings, it's kind of going to give you an overwhelming amount of information, but you can see how many parameters I can actually get into if I want to. So not only now can I enable retraction, but I can set my retraction distance. That's how far it's going to pull back. I can set my retraction speed. And again, these are not things that you need to worry about initially, but know that if you're having problems or print isn't coming out the way that you expect, you have these options at your disposal. And for a particular material, usually you can go online, do some Googling, and you'll find out, oh, when I'm printing TPU, for example, it has a huge propensity to kind of ooze and string. TPU is thermoplastic polyurethane. It's a flexible material. We'll talk about it. And so you may want to, so TPU is an example of something where you may very well end up tweaking your retraction settings to try and dial that. I can mess with cooling, my fan speed. This is something definitely worth mentioning because it covers one of the more common 3D printing issues that you'll see, and that is warping. And so what happens with warping is that when you print, you're relying on the first layer of your print to stick to this build surface, because that's what's keeping your print steady. That's what's keeping everything registered so that every time the print head moves over it, it's in the same place relative to the last layer, right? But you're melting this material and you're getting it really hot, laying it down, and then it's cooling. And as it cools, it wants to, when you got it hot, it expanded. As it cools, it wants to shrink. And so as those lower levels shrink and your upper layers are still hot, it introduces stress within the part, and the part starts pulling on itself. And if those forces build up too much, then it can actually start to curl off the build plate. This is super common and super frustrating when you're like 3/4 of the way through a great looking print and then you see it start to lift off. PLA, I don't see it as much, but when you deal with other materials, that's when you, like a nylon, that's when you'll start to see it. And so a big determinant of this is what's going on with your cooling, because you have a fan on your hot end, and you also have a fan that actually projects air onto the part usually to try and get that material solidified as quickly as possible so it doesn't creep or ooze on you. But if that's happening too fast, or really if it's hardening but then getting all the way cool too fast, that's when you can run into warping. So you can adjust those fan settings. The other and actually probably more effective way to deal with warping is to control your build environment. So the 3D printer is heating up the hot end in the build plate. But if you see a lot of warping in your prints, you may want to consider printing in an enclosure and keeping the actual surrounding air hotter, because that'll help you with those cooling issues by keeping the whole part at a slightly elevated temperature. And so you guys have
a Methodex here that kind of does some of that.
Okay. And honestly, so because there are other heating elements in play, you usually don't need something that's monitoring the build temperature. It's sufficient to just enclose your printer. Now, you can find videos on YouTube of people printing in like a cardboard box. not going to recommend that because again, there are safety implications. But there's some DIY enclosures out there, things that you can look at in terms of building with plexiglass. I think, does the WellSpot have sort of an enclosure?
Yeah.
Okay. So you can look at the equipment that you have at your disposal, and one might be a better option than another. Here's our support category. We talked about that. Build plate adhesion, again, this is also related to warping, and it's critical for successful print. Know that you have a couple of options in terms of adhering to the build plate. So if you can get away with it, just using the base of your part is the best way to do that because you have nothing extra. But you might run into a case where, let's say I'm printing this guy and I'm printing it in this orientation. That's not a lot of surface area for me to stick to that build plate. So it's much more likely that is either going to lift, or sometimes you can even see the extruder kind of clip the top of the part and it'll push it off of the plate. And so I can add features to help me keep that secured to the plate. And so the common terms you'll see is a brim. And what that's going to do is just add a single layer of material that kind of extends out from the cross section. And let me see if I can slice that and show you. And then there's also another form called a raft, which is the same exact idea, but it actually builds a few layers of material up before it even tries to start printing the part. And it's going to give you an even stronger connection to that build plate. It's more expensive, again, in terms of time and material, so it's a trade-off. This other stuff is getting a little out into the weeds, so I won't cover it today, but if you guys have questions, please ask. And so when we're happy with what we see, we'll hit the slice button, and it's going to crank on this and do all of the splitting up into layers that we talked about. And so now that it's done, you can see the summary information down there in the bottom right. So it's telling me, okay, you're going to use 63 grams of filament, and the estimated print time is 7 hours and 46 minutes to print these 2 test pieces. So now I can do a couple of things. I can either save that to a file, or usually what ends up happening is I save it to a memory card that's going to then get inserted in my printer. I can also, if I'm interested, take a closer look at what it did to slice that geometry. And so here, one of the most noticeable things is that you can see the build plate support that it's at. So see that brim around the outside? That wasn't there before, and that's purely to make sure that these parts stick to the bed. And then if I am curious, like let's say I kind of want to know what the infill pattern looks like that I've chosen, I can use this slider on the right and walk down through the layers. Oh, there we go. And so now I can see what my part looks like on the inside. And so, you can see this vertical column here. It's pretty sparse infill. Probably doesn't matter for this guy, but if that was something that was going to be load bearing, I certainly would want to change that before pressing go. And so that's just kind of that's an insight into how the slicing process works. This third tab, monitoring, that's if you have an printer. So it's kind of an optional extra. But when I'm happy with this, I will save it. And when I do that, you can see that it's going to save it as a G-code file. So those are the machine instructions that I talked about. And that's exactly what the machine needs to do its business. So that's hopefully a decent overview of the slicing process. Do you guys have any questions on that before we move on? Okay. So I mentioned a bunch of things to think about depending on your material. And let's talk for a minute about those materials. So we went over polylactic acid or PLA. Again, it's the most common material you're going to see, and there's good reason why. So it's extremely stable. It's easy to print with. It's cheap. That's a good reason. The downsides of PLA are, there's a few of them. One is that it's not particularly environmentally stable, so it'll degrade in sunlight. It actually is kind of, it's more degradable in general. Like it's technically a biodegradable plastic. I mean, I think on the scale of like decades, but it will go away eventually. And it also tends to be pretty brittle. So if you'll notice, actually, I think this guy must have gotten dropped at some point, and many of these little posts did not survive. And you can, if you want, you can take one of these, and if I just bend that, it's gonna snap off. So as an engineering material, it's probably not ideal, but for form and fit, it's great. And if that's all that I'm going for, if I'm going for something decorative or anything that doesn't have a load applied to it or doesn't have applied stress, PLA is great for stress. As you move into kind of higher material classes, you'll see ABS is a common one. You'll see a lot of nylon, which is not on this chart, but those are popular for really the same reasons. They usually have much better strength, they're much tougher, which means they stand up to abuse, and they tend to be more ductile. So they can take more bending and deformation before something bad is going to happen to them. ABS has great chemical resistance. ABS also has another unique feature that some of you might be interested in, particularly if you're making either models or parts that are cosmetic. And so, and that feature is called vapor smoothing or vapor processing. What you can do is you can print it apart in ABS, and you can stick it in, or you stick it above a bath of usually acetone, but some kind of solvent. And the vapor from that solvent actually melts the surface layer and gives it like a great mirror smooth finish. And so this actually was this is a piece that went on a visor system that we developed for some local college football teams, and it was a traumatic brain injury detection system. So they had like a headset and a tablet, and they could be assessed on the field when they're taking a big hit. This went through a multi-step process. So we did the vapor smoothing, and then we applied what's called hydrographics, which is where you dip it, and that's what gives us this big carbon fiber look. But you can see that this surface finish is incredibly smooth, and that was the only operation that was done. And if you turn it over, you can see that the layers are still very apparent, where we did not perform that process. So that's just kind of a unique thing to keep in mind. It's nice for intricate parts that you want to smooth, but you might not be able to stand or something very easily. I will talk briefly about Ultem. So this is a very high grade FDM material. You'll see it very commonly in use on either industrial printers or from some of those service bureaus like Stratasys or the big name 3D printing companies. Very strong, very durable. And this is actually being certified for parts on aircraft, both in commercial and military aviation. And then the last one that I will cover that kind of rounds out the common materials is TPU. So thermoplastic polyurethane. I'm trying to think of a good example, like the wheels on a grocery store shopping cart are typically going to be PU. This stuff is flexible film, and so you print it and it's still bendy. These parts are really small, so this has got some. So you can see now all of the filament is going to be pretty floppy, but just because it's thin. But this stuff, you can see I can bend it like an uncooked piece of spaghetti, and that's pretty much the durometer or the hardness that it's going to be after printing as well. So this is a great option if I'm looking to do things like make gaskets or interfaces between parts. These actually are an example of that. So I have an old car at home, and it has a bell housing inspection port. Well, in infinite German engineering wisdom, they put that inspection port at the top of the bell housing in the engine compartment, and it's actually a little bit magical. It creates a small black hole that is guaranteed to suck any screw or piece of foreign matter into it whenever you're working on the car. So this is a piece that I printed where I can just plug up that hole, and because it's flexible, it compresses in there nice and neat, seals out any dirt and debris, and I don't have to worry about it. So you guys can take a look at these more closely as well. And this is just something that's worth noting down here, is that whenever you're using a new material, just do a little survey of what the recommended settings are. And so Cura will try to take care of that for you, but there's quite a bit of variation in between vendors and types of material. So even if you're dealing with two different types of ABS, if you get them from two manufacturers, one of them might want you to print that ABS at 230 degrees Celsius, and the other might say 240, and that can actually make a huge difference. So it's worth doing the research. So let's talk about the biggest thing in FDM materials. So who can tell me what it means when something's isotropic? So you are right on, but flip it. So when it's stronger in one direction than another, that's anisotropic. So isotropy means the same in all directions. And anisotropy is the opposite. And what you will find is that really, no matter what you are printing, FDM tends to exhibit some pretty significant anisotropy. And so what that translates to is that because it's a layer-based process, I have different strength and different properties in my X and Y plane, which is what we call the plane of the build platform, versus my Z axis, which is up and down. And the reason why is you can see here, this is what they did here was they printed a bunch of tensile test material coupons in all these different orientations. And then they cut them up and they took a microscope picture. And this is the result. And you can see that as the orientation varies, these dark spots are voids in between the layers. And so that's where, particularly from layer to layer, you're much more likely to get gaps that don't get filled in all the way. And that's going to lead to decreased strength. And so this is the resulting tensile test. You can see in the Z-axis, my peak, my strength at failure is, what is that? That's like a third, maybe closer to 40% less than in my X direction. It's a little bit less than in the Y, and my elongation before break. So the amount that it's going to, the amount that I can flex it before breakage is much, much smaller. And so that's something to pay attention to if you're doing something that is carrying wood, because you may want to change your part orientation to maximize strength accordingly. You can find a lot of interesting videos online actually where people are doing like, they'll print little bridges and put weights on them. And it's incredible the difference in load carrying capacity just by changing the way that you print something. All right, so I think once you've covered all the pre-processing, now we're at the print process. And I think we've covered a lot of what's on this slide through talking through it in the slicer. But really, I mean, when you're printing, you want to monitor what's going on as best you can, and you might have to iterate. And that's the beauty of 3D printing, is that it's super easy to iterate. And so we've talked about all the things that you can and should tweak in order to improve your print quality. And remember that you can do this before you're trying to print something critical. And so like oftentimes when we set up a new printer, we'll end up printing 2 or 3 of these. and we'll tweak things in between, and that'll become sort of our set of new defaults. And Cura will let you save those as like a modified default profile. So if you get something dialed in for a particular material, definitely keep that around and use it again as your starting point for anything else. And we talked about the cardinal rule. If you're having problems, slow your feed rate down. All right, so I think we have a few more minutes. Okay. We're getting towards the end here, but this is a big and important category. And what we're going to talk about is all the different things that you might need to worry about after your print is done. So the very first thing is getting my prints off of the build bed. Sounds pretty simple. Usually is, but not always. So actually PETG is a material that was not on that chart. It's a great material. It's kind of sits in between PLA and nylon ABS. You can print it at slightly lower temperatures than nylon, but it's much stronger than PLA. But the one thing to watch out for with PETG is that it loves to stick to your build volume, to the point where I've actually seen chunks of glass get ripped out of a glass build bed because it's stuck so good. So sometimes you have to do a little work to get things off. They sell flexible, removable build platforms. Those can be pretty handy. For PLA, it's usually not a big deal. You can also consider using a sacrificial layer too. In fact, my printer at home, for some reason, PLA doesn't like to stick to my build bed. What I do is I put down a layer of wide painter's tape, and that becomes my build platform surface. It works great. And then you can kind of go down the chain here if you have a particularly stubborn print. Just remember that if you're applying a reasonable amount of force and it's not coming off, you might want to move to strategy B, C, and D before going full King Kong on it. Support removal, we talked a little bit about that. So if you're doing single material printing, it's all mechanical. You may have to get creative. Usually we start by removing the bulk of it with cutters or an X-Acto knife. And then if you need that critical surface finish, then you're probably looking at either doing some sanding, or a lot of times you'll see someone take a Dremel to get those last little nubs off. If you're using a separate support material, usually it's dissolvable. So there's a PLA compatible support material that can be dissolved in water. That's really handy. You just kind of put it in a bucket. It's good to have some circulation, but we've done it without it. And you leave it there for a day or so and it's all gone. Some other support materials that are compatible with non-PLA filaments, sometimes they need a solution bath. Usually it's a basic solution, so it'll have like some hydrogen peroxide in it. And they sell special machines that'll agitate these for you as well. It's a really good way to get supports that go away without a trace. But you also need to keep in mind that 3D prints are usually ports. So all those voids in the layers that we just talked about, they can also soak up liquid. And so if you are using this hydrogen peroxide solution to get support off, keep in mind that some of that stuff might still be in there. And in fact, it can be difficult to get all the moisture out of a print. In situations where that's critical, we've actually put prints under vacuum. And it's pretty crazy. Like, you can put them on paper towels, apply a vacuum, and you'll just see it start to bubble up, and those paper towels will be soaked, and you might have to do that a couple times. It's an edge case, but it's worth noting. And then, so once your support's gone, obviously you have a variety of ways to get the finish that you want. Most materials take paint pretty well. Sanding is also a really common way to get those layer marks off. Keep in mind that for either more complex or certain print technologies, you may actually have to do some traditional manufacturing processes as part of your post-process. So this is one example. This is a metal print out of an aluminum alloy. And this is a cover, cool looking cover, but you can see that
when you're printing in metal, you don't have the option of a separate support material. And so these are supports that it had to put in there to print these holes accurately. And that's metal that's then going to have to later be drilled out. And so you'll just want to, if you're doing something like that, and sometimes you have to on the polymer side, you have to plan for those operations when you're done. Let's talk about hardware. So eventually, if you're printing things, you're going to want to put them together in an assembly, and there are a variety of ways to do that. So you can print threads on an FDM printer. Sometimes they can even work pretty well, but keep in mind that below a certain feature size, it can be either too weak or just too problematic to really be useful. As a general rule of thumb, we try to not print threads that are smaller than M8 5/16 or so. If you're feeling adventurous, you could try for a quarter, but I'm not going to make any guarantees. If you're looking at that size or below, usually the way to go is using press fit inserts. And so you can get inserts that are just a straight press fit. They rely on pressure alone. They're usually knurled. That's going to be material dependent on whether they hold really well. Some do, some don't. If you want really the best option is to use a heat set insert. And so that is basically you stick a heat source inside the piece of metal that's providing you those threads. And they make special tools for it, but the most common use case I see is just soldering iron. Those are easy to get on hand. So you stick the insert in the top of your hole that's slightly undersized. You stick your soldering iron in, you wait for it to heat up and partially melt the hole, and it slides right in there, re-solidifies, and it's about as good as you're going to get in terms of fastening power. So this is one example. This is a cover or a lid, as we call it, for a radio frequency enclosure. This part's cool for a couple of reasons. It was printed in plastic and then given a metal coating after the fact so that it's conductive. But you can see here that all the places that needed these tiny screws, we've used heat set inserts in those places. You guys have any questions on post-processing techniques?
What was your first 3D print?
What was my first 3D print? I'm trying to remember. I think, well, at home, I bought an Ender 3, which is like the baby brother of this. And I think I might have just printed a Benchy, like that. There's a ubiquitous little boat that is everyone prints as one of your first prints. I don't know. So I did that, and then this came soon after, because one thing you'll learn is that it's very easy to go down the tinkering rabbit hole with 3D printing. So I think for a while I was printing more parts to put back on the printer than I actually was printing anything useful. And then slowly that changed. But so the last thing I'll mention is that, again, totally depends on your application. But if you are putting a part into production or in a real use case, obviously you can apply the exact same QA, quality assurance processes that you use in any other situation, but there are some additional considerations for something that's 3D printed. So when something prints, you can take a look and make sure that my layer adhesion looks good, that I don't have noticeable porosity, that my surface finish is the way I want it to be. And a lot of times, especially if we're doing a fit prototype, which happens a lot, we definitely we'll always put calipers on the overall dimensions afterwards, because sometimes you can have, this is obviously pronounced, sometimes you can have some subtle warping or deformation that you can't really see with the naked eye, but it might affect like my goal, which is to give me something that is the same size as a part that I am going to get machined later. And so that brings us to the end. I hope that you guys got something useful out of this. If you have any other topic that we didn't cover or any final questions for today,
please let me know. I'd be happy to answer. And also, Jay has our contact info. GTRI really, I would say our primary mission is to be a resource, a technical resource for the warfighter, and that ultimately means you guys. So if you have questions or get involved in this stuff going down the road, please feel free to reach out. We tend to visit Warner Robins pretty often. We actually have a field office right nearby that handles our sponsored work, but we always love getting involved in whatever's happening in this community. So thank you all for having me, and I look forward to working with you again.
Thank you, Kyle. That concludes our scheduled programming for today. I just want to touch a couple things before we go. First things first, this is all happening in the Spark Hub at Robins Air Force Base, and we are a resource for those people who are within earshot or on Robins Air Force Base who want to get things done. We're not here to do the innovation. We can't just innovate hardware for you, but we're here to help you if you want to innovate something. These doors are open. We can work with you. A question came up about shift workers. We can probably work to open our space to you guys. We just need some coordination time. So please let us know. You can find us on Facebook at Robins Spark Hub. And if you want to come in, we'll let you print something, whether it's for your job or just because you want a neat toy that you saw on Thingiverse. So please come in and try that out. The other thing, we are planning more events in the future. So make sure you follow us on social media and keep in touch so that we can let you know when all these things happen. If you have friends that you think might be interested in 3D printing or in any of the other things that we're working on, which is small UAVs or virtual reality training, please bring your friends in and just poke around. We'd enjoy having you. Finally, if you are an innovator at another base, reach out to your own innovation Spark Hubs. They're going to do the same things for you that we are trying to do for the people here at Robins. If you don't have one at your base, you can reach out to us or to AFWorks or any number of other organizations, and they can help you. Finally,